The idea is to once again take the OpenAI service documentation. So we will be looking at the OpenAI service documentation, and based on that, we will try to build a kind of a RAG system. Okay, and this is a very real world use case because a lot of organizations are actually focusing on this kind of an approach where you take the technical documentation of some company and you upload the technical documentation and users can query on the basis of that. Okay, so the approach will be very similar to the Tesla DB one that we discussed already in the general RAG discussion. So we'll upload the PDF file, we will create the chunks, we will store those chunks in the vector database as embeddings. And next time anybody can ask questions, like they can ask technical questions about the OpenAI language models. So next time anybody can ask technical questions and we will be able to generate the responses. So this is how the system will be designed right now. Okay, I hope the overall idea is absolutely clear how the RAG system will be designed. And you can see it's quite a big documentation. There are 914 pages. And as I was saying that you can go back and effectively use this in any of the, you can effectively use this in any of the real world applications. Any of the real world applications you can effectively use it on. Okay, so whatever we are discussing right now, you can even go back and use it on any of your personal documents. Let's say you can take some PDF file, you can take your resume, you have a list of resumes in a folder as PDFs, and you can effectively build a RAG system on that. And users can ask questions on the resumes that, hey, find out the top resumes where these skills are there. You can see how the retrieval augmented generation, the RAG-based approach can be extended to any kind of document. Okay, so this is the use case that we are covering. So now we break it up into two parts as I discussed. So the first part is, and eventually these are the kind of questions we want to be able to solve, right? You can see. So you're a solution architect and the objective is to be able to solve these questions. So we should be able to, users should be able to ask these kinds of questions and you should be able to get the answers. So that's the objective. So we again break it up into two sections. First part is we do the vector DB creation. So the first part is we actually create the vector DB. So you can see this is the PDF file. We'll upload the PDF file. And this is the other part. You don't have to use a directory loader. This is what I was mentioning. You can straight away use a PyPDF loader. You need a PyPDF directory loader if you're uploading a folder. That was for the previous use case. But here we can directly upload the file. Even if you want to upload the directory, that's also fine. But the objective is that in the directory there will be multiple files. All the files will be loaded automatically. But you can instead use a PyPDF loader. So if you just have a single PDF file, the PyPDF loader will work. Okay, this is not the only way to read PDFs. There are multiple other libraries in Python you can use, but this is one of the approaches we have used. Okay, so then you chunk the file. We're getting 972 chunks. And next, what we do is we go and create the ChromaDB, the vector DB. ChromaDB is the vector DB that we are using, the open source vector DB that we are using. And the name of the vector DB is AOI_DB. So once we do that, the AOI DB will be created in my folder. It is the same approach. I'm not running the code once again. The approach is exactly the same. And then what we do is we go to the other notebook, and this is the part where we do the RAG solution. It's already uploaded in the drive. Everybody can see the solution section uploaded. And what here I'm doing is I'm going and loading the vector DB. The only thing I'm doing is I'm doing the API key, the endpoint URL. All these are the standard stuff that we have done. Make sure you change the model name because we have all used GPT-4 Omni, and we are loading the embedding model. Okay, and we are loading the vector DB. And this is a good way to test it out, right? If you want to test out whether your vector DB is working fine or not, it's always good to load the vector DB. So step one, load the vector DB, and step two, try to see how many chunks are getting created. That is a good idea. That is a good approach to use. Okay, so always try to load the vector DB and see how many chunks are getting retrieved. So you can see the retriever I have defined as it will retrieve total 5 chunks, right? So that is how I have defined the retriever right now. So the retriever should be able to retrieve the top 5 chunks. Okay, so that is how I have instantiated the retriever right now. That's the idea. And you can see that we want to be able to retrieve the top 5 chunks right now. Okay, it's a good idea to check whether your vector DB is loaded successfully or is even created successfully by checking the retriever. Because if your retrieval is flawed, then everything else downstream will be flawed. So if your RAG is giving an incorrect answer, please remember, do not blame the language model. Don't blame GPT-4o because GPT-4o is not giving the answer. The actual answer is retrieved from your vector DB. So if there are any flaws in the RAG application, the first uh, investigation has to be on the vector DB. You should question how the vector DB is created, whether the indexing is correctly done, whether you're saving the data correctly. All those things have to be talked about. And we will discuss that approach as well, advanced retrieval techniques, and what are some other advanced strategies that can be used. Rest of the part is very similar. You create a very detailed system message, which most of you were able to do very nicely, but I have made it a very detailed. You can see, you can use the system message. You can see, I basically copied the problem statement. Whatever problem statement was given, I basically copied that. Okay, this was also one mistake I found some of you doing. Just to summarize the idea, this was a mistake I found that some of you are taking the same system message as Tesla. If you have a wrong system message, even if your retrieval is fine, the LLM will not be able to give the right answer because it is getting confused. So if you say, okay, give me the thing from the annual report, the LLM will get confused, okay, because it doesn't understand what annual reports are from this technical documentation, right? So make sure you have a right system message. So all the components have to work in sync. Even if one component is going wrong, then it will be a problem. Okay, see how we are making it very detailed. What kind of questions the user will ask. There are specific rules that I'm setting. That is the whole idea of a system message, right? System message should have all the different terms and conditions, the guardrails. Okay, although there are separate guardrail models we have, but even in a system message, you can specify some basic guardrails. Guardrails means restrictions or constraints. What things can be done, what things cannot be done, what kind of outputs cannot be generated. So all those are basic restrictions and constraints you can put as part of your system message. Okay, so please be mindful of that, that this has to be very, very detailed. Rest of the parts are exactly similar to what we talked about, user message template, retrieving relevant documents. And if I go and ask this question, what are the requirements for the indemnity clause to be applicable in case of a copyright claim? We are testing the retriever, and the retriever has indeed retrieved the top 5 relevant chunks. You can see the top 5 chunks are retrieved fine by the retriever, and we can see that we can test it out. This is a good first round of testing we can do. And once this is okay, now we can compose the entire prompt. Okay, so this is the user input. Here we have concatenated the user input with the retrieved context. This becomes the complete user message. Mind you, the entire user message is a concatenation of the retrieved context, the 5 chunks, plus the original user question, which is this one. What are the requirements, right? So this is the whole user message. We have the detailed system message that we wrote above. And now we are back to the chat completions create. This is the standard way how we are doing it. Okay, and because this is a factual application, I'm setting temperature equal to 0 because there should be no variability, right? It's a factual use case. So if I ask you what is the pricing of a GPT 3.5 turbo model, it is not, the answer cannot be variable. It's a very fixed cost. See, today if I ask you what is the pricing of ChatGPT Plus, ChatGPT is $20 per user per month. There are no two ways around it. If I ask that question, it is not that someday you will say $20, another day you will say $21. That we cannot afford. It is one and only one answer. We cannot have two different kind of answers there, right? So that's an important thing to keep in mind, that if you are asked this kind of a question, you will have to be very clear about the about the kind of responses you're getting, and the responses will not be variable. You will typically keep a higher temperature value for more open-ended generation use cases. But this is very specific factual question. So we'll typically keep a temperature value equal to 0. And it's also very common to use a try-catch block, try except exception block in Python, because if some users enter some wrong things, then we don't want the application to error out. We will do exception handling, and most likely some kind. This could be some content filtering error. We were seeing this yesterday also, right? Remember there was a content filtering error. So if a user enters some kind of explicit question, okay, some abusive things the user is asking, which is not relevant to anything in OpenAI, right? So they're asking some nonsense. People keep some random stuff they are talking about. So some abusive words they are using. So then the content filtering policy will be triggered. Okay. So in that case, the application will not error out. Only thing is that when a user asks that kind of a question, the application will say that, sorry, I encountered the following error. So that is basically a kind of a error handling that we have done here. And you can try it out. You can try it out real time in whatever code that you've written. You can try some random nonsensical text. Okay. And you will see the kind of responses you're getting. Okay. So this is a very basic use case that I wanted to show you. I've also uploaded the solution file for the other case study. Very, very interesting one. This is the Government of India case study. And this is also a very real world application. And as I told you, like whatever we discuss with respect to OpenAI and Tesla, the same can be extended to any kind of document, any kind of files. And it doesn't have to be PDF files. It can be any kind of text. Okay, the file can be present anywhere. It can be a database anywhere for that matter. Okay. So we have a Ministry of Finance report right now. This is the thing that we have again. And what we want to do is we want to build a RAG system on top of it. So I already gave you a question notebook, and this is the solution notebook which I have uploaded for your reference. You can go over it, but the approach will be very, very similar. Just that this notebook is a little bit more methodical. It's a little bit more methodical where we go over all the pieces. And what is the objective here? You're tasked with providing key highlights and details for specific questions from this report for your organization. This could be very helpful for government ministries and let's say things like the Planning Commission or the Niti Aayog as we call it now, right? So these kinds of institutions are basically involved in budget planning, uh, the country's economic development. What is the roadmap ahead? Or let's say some kind of RBI policies. The RBI has to decide a monetary policy. Should they reduce repo rates and all that? So a lot of those kinds of high-level macroeconomic decisions will depend on the government's finances. So the annual report is actually very, very important. Okay, so these are all very real applications we are talking about. Okay, how helpful these kinds of systems can be. You can see the approach is very similar. Again, we load the PDF file. We are using PyPDF loader. The solution is given to you. You can just straight away run it from here. So we are creating 799 chunks. The number of chunks is again very relative. Okay, so you have to again test it out. There are different chunkers are there. So don't try to have too many chunks and don't try to have too less chunks. So the number of chunks is again something you need to keep optimum and you need to play with it. Okay, if there are too many chunks, the retrieval will be a problem. If there are too few chunks, then doing the chunking itself is useless. Okay, so imagine what is the best case scenario. The best case scenario is we don't do any chunking. The whole document is one chunk. That's the best case scenario, right? So here we have a 400-page PDF file. So we say that entire 400-page PDF file is one chunk. Now, if I do that, then there is no need for a RAG solution itself, right? Think about it. If I say that the entire document is one chunk, then there is no need for a RAG solution because every time you ask a question, that only one chunk will be retrieved. And now it is up to the GPT model. We are putting the entire focus on the GPT model to generate the answer out of whatever chunk I've given it. And what is the other risk of having a single chunk? The other risk is that you end up sending the entire data as a context. That is the other risk. So doing the all this RAG approach itself is useless if you have a single chunk. So idea is to have many chunks. But the other extreme is if you have too many chunks, then also it's a problem. Why is it a problem to have too many chunks? Because imagine, if I say I have a million chunks, if I have too many chunks, then each of those chunks become very fragmented. There is very little information that is present in each and every chunk. That is the other extreme that is possible, right? So one extreme is that we have a single chunk that is anyways useless because the idea of RAGs is to create chunks, right? The other extreme is, imagine, I'm just taking a random case. Other extreme is every character is one chunk. Can you imagine? Every character is one chunk. Maybe to help you visualize this a little better, I can show you a beautiful example to help you visualize this a little better. So let me share a beautiful example with all of you. So this is a visualizer for the chunk, okay? How the chunking happens. And you can see this one. This is a sample text I have. If I say the chunk size is equal to 512, this is the general one, right? So I'm just keeping a general chunk size. Let's say if I say 64, or if I say 128, this is the general chunk size, okay? It's a general chunk size I'm setting right now. And you can see, I think the chunking has happened decently, right? Every two paragraphs, we are getting a chunk. Can you see? The moment I say 680, you can see every two paragraphs is one chunk. This is chunk 1 in blue, chunk 2 in yellow, chunk 3 in orange, chunk 4 in this. And you can see how we have done the chunking right now. Now, the problem is if I say chunk size 1, this is useless, right? See how many chunks I'm creating. This is what I said is a problem. So this is something we should never have. We should not have like every character is one chunk. Because imagine if you're saving this in a vector DB, how funny the vector DB will look like. So you will have a character called O, okay, or you'll have a character called, N, E, and you will create embeddings for that. This is useless, right? So the number of chunks should be optimum. And that again has to be tried and tested. There is no one way to answer this question. It has to be tried and tested. There are different ways you can do chunking. And there is even something called semantic chunking. The one that we are doing here is like a fixed size chunking. You're chunking based on 512 characters. If you see the code, that's what we have done, right? Mostly that's what we have done. We used a fixed size chunking. Can you see chunk size equal to 512? This is exactly what we did here. We are saying, okay, every 512 characters, you create a chunk. So every 512 characters, you create a chunk. So from here to here, there are total 512 characters. Okay, so every 512 characters, we are creating a chunk. But we can change that. And there are different ways we can do chunking. Chunking can also be done based on other approaches. So chunking can also be done based on semantic techniques. We can also do something called semantic chunking. You know what is semantic chunking? So very briefly, I'll I'll show you. Semantic chunking basically means that you chunk based on the semantic meaning of the semantic meaning of the articles. This is the general idea. So what we did was we did fixed length chunking, fixed size chunking on the right hand side. So every 512 characters we have a chunk with some overlap. On the left hand side, what you do is you do something called semantic chunking or theme based chunking. That means you have the entire document, and based on some GenAI model, we are able to figure out what the different parts of the document are. So let's say if we have the Government of India annual finance report, that particular document will have different sections, right? So now based on different sections, the chunking will be done. So the introduction part will be chunk one, section one will be chunk two, and conclusions will be chunk three. So this can be in completely different page numbers. This can be completely discontinued, like the order of the words may not be, the order of the sentences may not be sequential. Let's say some part is taken from page one, some part is taken from page three. That can happen. Or let's say from the Ministry of Finance report, I create theme-based chunking. That is, there is one theme about GDP, there is another theme about finance, another theme about defense, because the government will highlight their expenditures across different categories, right? So I will create theme-based chunking based on different categories. So there are many, many different types of chunking strategies that you can explore. Just wanted to highlight that part. Anyways, so now you can create the vector DB. This part is the standard. We take an embedding model and we create the vector DB. The vector DB usually takes a little bit of time to create. And I also told you how to speed up the process. Go to runtime, change runtime type and names are GPU. Okay, so GPUs will be usually needed for the vector DB creation because we are using an embedding model and we are trying to take every single a chunk, and we are trying to use an embedding model to convert them into their embeddings. This part is actually very, very compute intensive. The part where we are using the embedding model and we are trying to convert the chunks into their respective embeddings. And that is why the GPU part will be needed. Rest of the parts are very simple. This is the system message specifically for the GOI use case. User message template will be exactly the same as we did before. And top five chunks are retrieved. And then the question we are asking is, what are the trends observed in this investment? Right? So this investment thing, and you can see how the LLM has answered it. Very nicely, the GPT has formatted the answer. So the five chunks that are retrieved are very random, but see how the GPT model has generated the answer in a very refined manner. And these are a few other samples I've given you. You can you can run this notebook and then you can try out these samples. This code will run exactly the same way. Okay, so provide an analysis of direct and indirect taxes. You can just run the code. This is what we will actually get. Provide the financials for the agriculture sector. I've already given the user input. What you need to do is you need to concatenate the user input with the retrieved context, add the system message, and just give me the complete response. That's it. Just hardly take 5 minutes as an exercise, which you can do later on. And the last part is where we did the evaluation of the prompt, the RAG application that we built, and we are using the groundedness judge, and we are using the relevance judge. There are two different judges we create, and we can see what kind of ratings the judges are giving. Okay, so this is the last part of what we actually did. All right. Now, moving on, what I want to talk about right now is another very, very interesting use case. What I want to talk about is another very, very interesting use case. We want to talk about how do we build multimodal RAGs, right? How do we go back and build multimodal RAGs? Now, what is a multimodal RAG? Let's talk about that for a minute. How do we basically build RAG systems with mixed data documents? Now, this is oftentimes a use case and a scenario that you will face in the real world, right? So this is oftentimes a use case or a scenario that you will face in the real world where you want to work with mixed data documents. You want to oftentimes work with mixed data documents. So in all the demos that we saw until now, Tesla, Government of India, Azure, we only had text data. But in a real world application, you will not just have text data. You will have text, you will have images, you will have tables, and these are very, very common things that you will have in a PDF file, right? If you think about a PDF file will also contain these kinds of data. Even our current PDF files, if you see, our current PDF files also contain this data, right? So some of the content, if you see the OpenAI documentation particularly, or the government of India report, the GOI report, if you see, many of the parts actually contain tables. Some of the parts even contain images. If you see the documentation, there are some pictures that you will see. Problem is the approach that we have followed right now that does not handle the pictures, that does not handle the tables. Now we would have thought that everything is getting working fine and successfully. No. The problem is whenever it encounters an image, whenever it encounters some other mixed data type that it is not able to recognize, our model has ignored that. So parsing is a very, very important part, right? So the vector DB creation happens a lot later. But the first part is how do you take that document data? How do you parse it? And then you do the chunking. And only after that you go ahead and vectorize it and save it in a vector DB. So one of the most important parts of building a RAG application or anything for that matter, whenever it comes to any kind of document type data would be to do the parsing and the chunking. Both of them go hand in hand. You parse the file, you make sure that you read the file properly. Reading and parsing are going hand in hand because when we say read, that means you're basically parsing. You're trying to understand what is there in the document or the PDF. And that is not just a text-based parsing. You want to parse based on other forms of data as well. So this is the very real thing that happens in a parser. And now I'll give you a small flavor in terms of what other kinds of parsing techniques are used in practice, what other forms of parsing techniques are used. So you can see that we are using a parser. And the parser is taking the PDF document and it is parsing the text separately. It is parsing the table separately. It is parsing the images separately. This is also a very common strategy that is used. Because as I told you, a PDF file will contain different types of data. It will contain text, it will contain tables, it will contain images. So a parser, what it will do is a document parser will take the data, will read the document, and it will parse the text separately. It will parse the images separately, and it will parse the table separately. And then the chunking will happen. I think the chunks we are already aligned with how we do the text-based chunking. It will chunk the text separately. The same idea that we discussed. We use chunkers. Every 512 characters, we say, okay, let's say as an example, page 1 is chunk 1, page 2 is chunk 2, page 3 is chunk 3 based on the text. So we create chunks for text. We can also similarly create chunks for tables. And a simple example would be one row is one chunk. I'm just giving a very ballpark example. Each row is one chunk or each table is one chunk. Think of it that way. So there are chunkers. Separately, the chunking can be done only for tables. And finally, we can also do chunking for images separately. So we can say one image is one chunk. So these are the two additional steps that we are putting in terms of mixed data RAGs. So take the document, use high-end parsing applications, and the one that I will show you here, the one that I will briefly show you here is something called LlamaParse. LlamaParse is very, very popular. Okay. I'll show you a small example of LlamaParse, how LlamaParse can be used to parse a multimodal kind of a document, a PDF, where there are different types of data inside the PDF file, how the parser can extract the text separately, it can extract the images separately, it can extract the tables separately, and then it will chunk them separately. It will create chunks of text, chunks of images, chunks of tables, and then for each of those chunks, it will do the embeddings. And the embeddings will happen separately for the text. And remember, there are different models for each one of them, right? We are not trying to do anything. We are not trying to create these models. They're all pre-trained models. Just like I showed you yesterday, there are the massive text embedding database MTEB benchmark, sorry, MTEB, massive text embedding benchmark, MTEB benchmark we have. So we've got text embedding models. Similarly, we have table embedding models and we also have image embedding models. So there are separate embedding models that will be used to create the embeddings for the text chunks, create the embeddings for the image chunks, and also create the embeddings for the table chunks. And finally, all that information will be part of the vector DB in an index manner. And now you can see how rich the vector DB will become. So now the vector DB has all the chunks and the respective embeddings, but this time the chunks are basically not just text chunks, but they also are image chunks. They also have tabular chunks. So different forms of data are now part of the vector DB. So this is how we think in terms of an application perspective, how we work with a multimodal RAG. Now, just to give you an example, you can actually see LlamaParse. LlamaParse is not very hard to explore. You can see LlamaParse in action. So LlamaParse is actually a very popular parser. There are many parsers out there, but LlamaParse is actually quite popular. You can go to LlamaParse and you can see at a very high level what they do. At a very high level, you can see that LlamaParse transforms unstructured data into LLM optimized formats. Very important, right? So it is able to transform the unstructured data into LLM optimized formats. So that is one of the things that LlamaParse is able to do. Okay, all of you can see the screen. Okay, so for example, if the original document looks somewhat like this is what the original document looks like on the left hand side. If the original document looks somewhat like this, after you use LlamaParse, the transformed document will look somewhat like this, what you're seeing on the right hand side. That is what the transformed document will look like. So if the original document looks like this, the transformed document using LlamaParse will look like this. And you can see how beautifully it has taken the chart. The chart is otherwise an unreadable data, right? This is usually not readable. This is not machine readable. I mean, it's not text, right? So this bar chart is not actually a text. But see how beautifully uh, the chart embedding models have understood what is there in the bar chart and how they have converted that to a tabular or a text kind of form, which the LLMs can understand. So parsing is actually a very important part. So all your chunking and embedding happens after that. But first you need to read the data, right? So that's an important aspect of what LlamaParse does, right? So I'll just show you, like you can have to log in. You have to log in and then you have to see how it's working out, right? So let's just see. They give you some free limits. Okay, I won't be able to show you every part of it because this is a paid application, but it's just for fun. You can try it out, and it's quite good. It's quite powerful, right? So this is the LlamaParse free plan that I've shown you right now, and you can also get the free plan. You can see if you click on it, you'll be able to see your usage, how much you've used, and what kind of thing you've done, right? And you can see there are three things that they give you. One is for index, second for extraction. You can extract information from documents, and third is parsing. This is what we are interested in. We can go to the playground. You can click on the LlamaParse playground, and you can actually see. There is also something called Llama Trace. This is all part of the Llama stack, by the way. Llama Trace is also a very, very popular thing for tracing, LLM trace. So it's basically used for LLM operations. So whenever you do an API call, so Llama Trace is used to keep a track of how many requests you're sending, any errors that are happening, all kinds of logs, how the language models applications are performing in production. So Llama Trace is very popular for this kind of LLM ops kind of stuff. Okay. Anyways, you'll see a lot of these applications which are starting with Llama, Llama Parse, Llama Trace, Llama Index. So they're all part of Llama. All right. Now, what you can do, you can try this out. You can upload any document and you can actually try it out. And what you can also do is you can set up an API key. The same way you can set up an API key. I'm not showing this part right now, but you can set up an API key and you can access Llama Parse from within your code. Okay, so this is just the playground interface, the user interface that you can see, but the same way you can do it in the code. And that is exactly what I have demonstrated to all of you in this particular hands-on. This is a very extensive hands-on exercise where I try to use a multimodal RAG for a research assistant application. Okay, so this is a very exhaustive demonstration which I've shown you, and this is what I will quickly take you through right now. You can all directly use this one. And just to add one more level of detail, in terms of what we are discussing. This is the NVIDIA blog, and I actually kind of like this article a lot. If you just see, if you scroll all the way down, here also they give a very nice blueprint for multimodal retrieval blueprint for RAGs on PDFs. Okay, so all these are very new ideas, right? So you can see NVIDIA published this in 2024. This was like less than a year back, right? So whatever we are discussing right now in the class is actually, especially the multimodal part, is very new. Okay, so Llama parse and all this is very new. It's not like text-based parsing has been there for a long time. But the other aspects where you take a complex PDF file and you have got lots of different types of data. So this is something which is very new. And just like we are talking about Llama parts, similarly, NVIDIA also gives a framework. And what is NVIDIA's framework? NVIDIA's framework is using the NeMo framework. NVIDIA has something called NeMo. Okay, and you can read about it. You can read about NVIDIA NeMo. So they use something called NeMo to do this. Okay, so you can read about the NeMo framework and how they use it. Okay, so this is the pipeline. I can open this in a new tab and show you. This is pretty much what we talked about, and you can see. Uh, so PDF documents, we are first passing it through the PDF parser, and this is where we can, either use NVIDIA's internal NeMo, or we can use LlamaParse. Other kinds of parsers can also be used. And what it will do is it will parse it. So if it is a text data, there is no problem. The text will be taken as it is. You can see if it is text, it will be taken as it is. And if it is an image, uh, the charts, look at this, tables as images, because the tables are pictures, right? The tables cannot be read. See, if the tables can be read, it is okay. But if the tables are there in a picture form, that's a problem. Then you need to convert it, right? You need to convert it. So that is the idea. You need to convert it. Okay. So what am I trying to say? Let me see if I can maybe explain this in a better way. Okay. So for example, look at this. See, sometimes, look at this one. This is the image, right? Now, if I go to, this is a PDF file, this is a PPT. I can convert it to a PDF also, right? See, this particular text I can select, right? Can you see I can select the text? So all the text in my slide I can select. Look at this use case, all of you. See, I can select the text, right? So this is actually text. This is actually text. But this one, uh, you can actually save it as an image also, right? So if I go to file, let me show you what I mean to say. It'll be better if I show you through an example. We can connect this a lot better. Okay. So I can actually save this current slide as a JPG file, and now you can relate to it a lot better. Okay. Look at this. Now if I try to select, can you select? See this? This is what I meant to say. So this one, if you see, I mean, for the human being, it doesn't make any difference because you will say, hey, Sayan, I can see the slide. But the moment you pass it through a parser, this can be read as a text. The machine can read this as a text. That is how your chunking was happening. It can process this as a text. Okay. But if you have a picture instead, if you have an image instead, the parser cannot read this as a text. I cannot select it. See, I'm trying to select. I'm not able to select. I'm not able to select. This is the image. So what you this entire thing is an image. Although this is a slide, I'm trying to copy. I'm not able to copy. This is the picture. It's a JPG file. You can't copy this. You can't read the text. You can't copy paste the text, right? That's the issue. And lot of times when you work with PDF files, if you have charts, you might have a chart where there is some text, but you're not able to copy the text because it's in an image form. And there, what you have to do is you have to use this kind of a framework, right? So the text will get processed normally, no problem. But if the page is in an image form, then there are two parts to it. One is there is a table as an image, and the second is there is a chart as an image. And so there are separate models that you have to use to, you don't have to use it. All these applications will do it automatically for you. There are separate models that you will have to use to convert your tables into a text form and convert your charts into a text form. That's the same thing that we saw in that original thing. No, remember I showed you that how LlamaParse is able to convert your bar chart into a text. So you're able to convert your image chart into a text, and you're able to convert your image table into a text. Now everything is text. You've got pictures, you've got tables, you've got text, and now the chunking will happen. NeMo is again specific to NVIDIA, but you can use your own chunkers. You can use your own embedding logic that we have discussed. We can use ChromaDB. This part is the same. And now we save the chunks in the vector DB. So we create chunks separately for the images, separately for the text, and separately for the tables. And now the other things will happen. Like this is the retriever. It will retrieve the chunks. The front end, the user will query, get the response straightforward. This is something else. This is what we'll talk about later, ranking, re-ranking. Okay, but rest of the flow we can understand. So this is just to give you an idea about the whole RAG pipeline in terms of advanced multimodal applications. So above part is the ingestion pipeline, how you read your data, how you parse, how you chunk, how you create the vector DB. This is often one of the most important and one of the most time-consuming parts. Once that is done, the retrieval pipeline is easy. It's easy. This is the easiest part. Now, This is the end-to-end application that I've tried to show you. So I've taken real data here. If you see, these are image papers. I'll download this and show you what type of data we have. And the objective here is I've shared the code in such a way that you can directly take it and run it. All these are perfectly working code samples. You can directly take these code samples and you can run it. But this is a more advanced exercise, so we won't be doing this in the session right now. But I have shared the exercises with you so that you can all try it out. The image papers, you can see these are real research papers that are given. Maybe for a minute, if people can read the business case. Okay, all of you can see this. Everyone has read the problem statement. So you can see it's a very real world use case where we are discussing how we can build a RAG application for researchers. And RAGs are a very, very good use case for researchers particularly. Imagine you're trying to research something, you're trying to write a research paper. And if you have done some research in your career, you will know it's very important to dissect information or retrieve information from different sources. Uh, Google was the go-to tool in the past, right? We have all used Google, right? We continue to use Google a lot. The researchers have to Google a lot. They have to go to different papers and different references, different links. They have to study different things, and based on that, they will do their research, right? So RAGs can be an excellent application area in this field. So what we are saying here is uh, the researchers can write certain queries. They can enter certain queries, and based on that, the RAG assistant will be able to automatically fetch the information from all the research papers and give them the answers. Okay, so this is a very simple use case where I only am showing you 5 PDF files, but you can imagine a more real world use case where we have tens of thousands and millions of documents, millions of research papers are listed in this particular portal, and anybody from the university or the organization can go and write a query and get answers based on their query, based on all the research papers that are out there. Okay, this could be a very, very good practical application. Just to show you some example files, you can see this is what the example files look like right now. So this is the first one, some functional vignette, memory part 2, role of medical temporal lobe, whatever. And you can see this is real world data. It's actually a real research paper. I've taken from the page number 846. It's a huge one actually. So I've only taken some small sample of it because these are all huge, huge papers. And this is the part I was mentioning. You can see these parts I can copy. I can copy and paste it. But these parts I cannot copy. Although this is text, if you see, I cannot copy. Like amygdala, hippocampus, okay, uh, entorhinal cortex. I cannot copy. This is actually in an image form. Okay, this is all very real applications. This is the image. So this document is a combination of text, pictures. You'll see some tables below. And if you try to use your normal parsers, you may not get errors, but it will not work correctly. This is one more example. You can see. Again, there's a lot of text data we have. And see, the data is some pictures, some references, some links, some table. This is a table actually. But this table is in a text format. But this is still a table, right? See, this is all images. This is in a text form. But some of them are not in a text form. So a lot of these practical applications we have here, actually. Now, what we want to do, we want to build the RAG system. There is something else we are doing in this particular exercise. We are actually installing requirements.txt. Okay. So all this while, if you see in all the previous code snippets, what we were doing, we were just using directly, we were doing pip install all the individual libraries. But here what we are doing is we are actually doing something called requirements.txt. So requirements.txt is basically a text file. So you can see what the requirements.txt contains. It's actually a text file where all my libraries are highlighted. This is a very practical way how things are done in the real world. Okay, so if you're actually trying to deploy applications in Python or in GenAI or data science or anything for that matter, so this is how you will do it. You'll not do pip install individual library names, but you will actually create a requirements.txt file, and in that requirements.txt file, it's a simple text file. You will list out all your packages. You will list out all your packages in this one single file, and then what you do in the main Jupyter notebook is you just go and say pip install requirements.txt. So see, pip install requirements.txt is what I'm doing. So automatically all these libraries will be installed. So whatever libraries I had here, all these libraries will be automatically installed. So right now I'm doing in my local machine. So we are not realizing the benefit or importance here. But the moment you deploy this application somewhere else, which I will show you in the second part of the session. So once you deploy this application to some other environment, okay, so once you actually do a real-time deployment to some other environment, so there you need to install the same packages. The same packages need to be installed there also, right? So there the requirements.txt will be a lifesaver. So there you don't have to individually install the packages. So whatever packages you have saved here, the same set of environment will be created there. Okay, yeah. But there are other ways to do it. You can use Docker containers and all that can also be used. So we want to ensure that whatever libraries and versions we used in my dev machine, so the same thing is used in my production system. Otherwise, your code will break. There are some things that you use which will not work in production. Okay. So unzip research papers, image papers.zip. This is the same approach that we used before. So you take all those PDFs and we use the PyPDF directory loader. This part is the same as what we discussed before. You can see. And this is the embedding model. These parts are very, very similar. And here I've actually used LlamaParse. Okay, you can go through this code. You can run the code as it is. It will run absolutely fine, but it will take a lot of time because the parsing part actually takes a lot of time. So you can do this later on after the class. But you can use LlamaParse to do the parsing and see how it actually parses images. I've saved the outputs here so that you can see what has happened. This will help you understand what has happened actually. So see how we parse the image object separately. The images are separate. The tables are separate. You can see. So we have parsed the picture separately. These are the images. You can see. These are all the images we have parsed separately. .png, 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 height, width, and where the image is present. X, Y, W, H. This is the bounding box actually. So we have the image name. We have the width and height of the image. X, Y, W, H of the image. Where the image is present in the whole page. So similarly, we have also extracted. These are all the images you can see. So the first pass, we have managed to go through all the PDFs and extract all the images. And the next objective would be to take these images and create embeddings out of it. Okay, and there are different embedding models that are there for images. So people who are coming from a slightly deep learning neural network kind of a background, you understand there are CNN models that are used for this. There are convolutional neural networks that are used to take a picture, and from that image, we can create feature vectors. We can create image embeddings from a picture. So those are all pre-trained models that are there for images. So we don't have to worry about that. That's another topic altogether. But idea is once we extract the images from the respective documents, we can use embedding models to take these images and extract embeddings out of it. Similarly, we can also do the same thing for JSONs. These are basically the, these are the tables, the tables. There are some JSON objects that are also there, by the way. Anyways, we can do the same thing for the JSON objects also. There are tables, and this is how we extract from the tables. Okay, you can see. So the LlamaParse will do everything for you. We are not doing anything manually. So the parser has automatically extracted all the pictures, all the tables, and see these are the tables we have right now, and all the text. So LlamaParse has done all this for you. Okay, so now that we have extracted and separated all the required modalities, let's process each of them starting with text. So now we start the processing. So we save them in the Chroma DB now. We do the chunking. See, we take the text and we create the chunks. 883 chunks are there. And now we save it in the vector Chroma DB. Straightforward. And now the rest of the process follows. Okay. So some of the parts here are related to advanced retrieval techniques, which I will talk about later. I will talk about advanced retrieval techniques later on, but you can get the idea what we are trying to convey here overall, generally. Okay. I've also explained the semantic chunker. Remember, I talked about something called semantic chunking. So semantic chunking is basically not a fixed size chunking. So far, what we discussed in the demos was something called fixed size chunking. See, instead of chunking the text with a fixed chunk size, so we were doing that, right? So every 512 characters, we try to create a chunk. Every 1024 characters, we create a chunk. So instead of chunking based on a fixed size, what we do is we chunk based on the semantics, based on the meaning of the documents. So that's the way how we go about it. So we instead chunk based on the meaning of the documents. That's the way how we do this. Okay. So this is the chunking that we have done. And then rest of it is very, very similar based on some advanced retrieval techniques. So once I discuss this part of the discussion now, this will be another 15, 20 minutes what I will talk about. So the rest of the notebook just talks about the advanced retrieval techniques. So this is the demo of the advanced retrieval techniques. But otherwise, the most important objective of this particular notebook was to highlight to you how we work with a multimodal system. So if we have different types of data, if we have tables, images, text all together, how we can use something called a LlamaParse to take them separately and create embeddings for them separately, right? So that's the way how we can work it out. Okay, and you can see here just one sample example I wanted to show you how the final system will work. This is a lot of code I know, but it's all the same. You can see the final thing, how it will look like. This is the RAG on the multimodal data that we have done. This is the final retrieval that we have done. You can see how the RAG system will actually work out. You can see how to do LTD, LTP, and LTD induction effect, synaptic strength, and morphology. So this is again some completely lot of technical jargon. I don't think anybody in the class understands what these things mean. Neither do I. But this is again some biology field, I think. Okay. So given this question, what we want to do, see, we want the retriever to retrieve fetch at most 3 images for the query. So we want to fetch the pictures and we also want to get the text. So this is what actually happens in a multimodal system, right? Today, if you when you go and run these queries in a GPT, so what happens in a GPT model is also this. So the GPT model also does something, exactly, something very similar to this. That's the idea. Okay. Yeah. No, 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 no. It's not open source. It's only open source up to a limit. They have a free tier. They have a free tier. You can just log in with your Google account. There's a free tier, but it is paid. Correct. But there's an API key. There's an API key we have to provide. See, that way even OpenAI is also a Python package, but that doesn't mean you can use OpenAI services for free. Make sense? Yeah, 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 yeah. You have to. There's a section you will see that I actually did not give the API key here, but you have to mention the API key. Otherwise, it will not work. Okay? Yeah. So you have to go to the website and there's a way to create the API key there. Okay, so this is the final result that I'm getting. You can see how to do LTD and LTP induction. So when I write this prompt, this is the kind of response I will get. Okay, so you will get the text response. So the model beautifully explains what is LTP and what is LTD. It gives a text response from my document data, and it also gives me an image response. Remember how I told you fetch at most 3 pictures? See how it has fetched me the 3 pictures. Beautifully, it has answered that question. So it has explained the topic, and it has gone and explained to me what it is. Okay, so now you can relate it back to that fin.com that we were discussing yesterday. Remember that fin.com where I said what is a confusion matrix? And I think slowly you can start to relate to what's happening. So there also it is some kind of a retrieval technique where it is based on the question I'm asking. On one hand, the model is retrieving the text answer. It is explaining what is the confusion matrix, what is the classification report, and it is also returning back one picture. It is returning back one image from its repository, from its relevant chunks. It's giving me one image, which explains what the confusion matrix actually relates to. Okay, so that's the way how we can understand how the system is working behind the scenes. Okay, so this is actually a beautiful application. You can see here I've actually kind of completely done the whole thing from scratch. So how to do LTP and LTD induction effects, synaptic strength and morphology. So this is the kind of result I want. So user will ask this question and the model will go and answer it in text and then also give the pictures. Beautiful, right? So, and also give the table. Here I also did the entire thing. So first, based on the question, the model will return the text answer, it will return the image answer, and it will also return some tabular answer. It will also give a table which kind of highlights something related to that LTP, LTD. God knows what that means, but whatever that is. Okay. So you can see that this is how we did the whole end-to-end process. Wanted to share this because this is the kind of stuff that everybody will do in the real world. The real world, when you work with complex data, this is the kind of stuff that all of you will work on. Okay. Now, from here onwards, we want to shift our focus to advanced racks. And before that, there is one other very small demo I wanted to show you. I have already uploaded that in my main folder. This is something called Amazon product reviews. Very similar. The use case is very similar to what we discussed, but there is just one or two couple of ideas that I wanted to take you through as part of this whole thing. So let us see. Okay. Now, what is the business context? What is the business context of what we are trying to cover here? Let's take a minute to discuss the business context, right? Because whenever we solve some new things, we should understand the business context, what we are solving, right? So in all these exercises, that's the approach we have followed. First, we try to understand the business context. What is the problem that we are solving? And then we discuss a technical approach and how we went about it, right? So what is the business context here? So let's go to Amazon for a minute. That's why I kept Amazon open, right? So when we go to Amazon, when we search for something, so what naturally happens is, we go and we search for some tools and some certain things, right? So what we do is uh, let's say you want to search something on Amazon and you want to search for, like normally we search based on a product name, right? So if I go and search for S25 Ultra, what happens is I get this product S25 Ultra. But what I want to do is I want to go and search based on natural language. So what I want to do is I want to search based on natural language. So I want to do some kind of an NLP based search. Some kind of natural language based search is what I want to rather do. That is the objective here. So how do we go and do some kind of a natural language or NLP based search? And that is exactly where the RAG part will come in. Think about it this way. Amazon, let's say, has a product repository of 1 million items. I'm just giving an example. Let's say there are 1 million items in the Amazon catalog. 1 million items across categories, across electronics, across groceries, across beverages, food, whatever. Okay. There are total 1 million items that are there, 1 million products that are there. And let's say every product is a chunk. So when you want to eventually create a vector DB, what kind of data will you have? You will have the product. Okay. So you will have the product. Think of it this way. Every chunk will be like a product. Think of it that way. So when you go and eventually create a vector DB, you will have a product description. And with respect to the product description, you will have the embeddings. So just to highlight this a little better, if you think of this as your vector DB, every row will be like a product description. A description will be text, right? So you'll have a description of the product. What is the product talking about? This will be the complete text. And there'll be some references to the ID. What is the ID of the product? This will talk about what is the product title. So all the text components will be added as part of a description. So text will be the product itself. What is the title of the product? The description of the product, the return window, everything. So when you click on a page, all the stuff that you see. So when I go to this particular page, Samsung S25 Ultra, all the stuff I see here, this entire thing is part of my text description. So we will have a description and we will have, and for the description, we will have the embeddings. Right? I hope you can understand the way how we will maintain the data here. So every row will be, let's say, one product, where for the description of the product, we will generate the embeddings. But if we are building a truly Gen AI based application, what we want to do is, given a user question, the model should go to the vector DB. So we should, based on the user query, we should go to the vector DB, fetch the relevant chunks. That means fetch the relevant products which are matching this particular user query, fetch those relevant products based on their descriptions, because mind you, the descriptions are basically the chunks now, right? So fetch those relevant products, the top 5 products or the top 5 chunks based on their descriptions, and return that to the result end user. So that is the application we are talking about. And this is not just for e-commerce. We can do this for any kind of thing for that matter. So next time you go to Netflix, you can imagine how you can go and search on Netflix now. Okay, incredible, right? So you can go and do the same kind of search even on Netflix. So Netflix also nowadays, what we do is we search based on, we usually have to search based on the name of the movie. But you can have a generative AI based search even on Netflix. So the same concept can be used for searching based on multiple platforms. Let's say you want to search some kind of a song on Amazon Music or Spotify. What you can do is you can describe the song. You can say, hey, I want to listen to a song which talks about this, talks about roses, talks about road trip. I want to listen on a road trip. You can give a descriptive 100-word sentence, and Spotify will return the most relevant songs which match that sentence. So these are the true power of generative AI based search. Even something that Google is trying to do. Google Photos, if you see, Photos is also trying to incorporate this feature where you can describe your photo in English, and based on the RAG-based approach, it will return the relevant photo results for all of you. Okay, and this is exactly what I try to do in this demo. You can see. So I try to this is my entire product sample database that I've created for you. All of you can see. This is a demo database. It's a demo database. So we have got the product title, the product description. Every row is a product. That's what I told you, right? So each and every row is a product, and you will typically have this data very beautifully structured in a typical relational database. So in a relational database, you will have this data stored. So every row is one product, and you will have the product title, the product description, the price, and all that stuff, right? And if you scroll all the way down, what we are doing, we are just creating the chunks. We are creating one single uh, text. So the initial pre-processing part is very important. See how we are combining this entire stuff. So we are saying plus, and we are getting a combined text. So I'm cutting the text. So the final product description column contains Parag Fragrances, Ambery Chandan UD perfume, long lasting perfume by Parag Fragrance, which is this. And you can see this product is available from the company Parag Fragrances at a price of 749 at a discount of 12.25.1. So these are the last two things that I've actually added. Okay, so product data, the brand name, the price, and the offers. So we have the description, which is anyways coming from the initial part. And only additional part I've added is, you can see, this product is available from the company. This part, Parag Fragrances is the brand. At a price of 749 is the price placeholder. And at a discount of 25.1 is the discount, offers. Offers is the discount. So this is how we have constructed the complete description text based on the table. So from the table, I've basically created this one. So this entire thing is basically one product description. And this will eventually become a chunk in my vector DB. So when I go and create my vector DB, this entire thing will be part of my chunk along with two metadata. One will be ID and one is price. This is one additional part that I'm talking about, metadata. Oftentimes, you will do metadata-based search. So it is actually a good idea to have some metadata as part of your search. Okay, so see how the documents will look like right now. Every document is like a chunk. Think of it that way. You can see the page content, professional grade face peel. This peel simulates collagen protection, whatever. All this is there. See, this product is available from the company LlamaParse. This is the brand name, mind you. We created the whole description this way, right? At a price of, okay, sorry, let me select it again. At a price of 799, this is the price, and at a discount of 65.05%, which is the offers. So this entire thing is the complete product description column. Okay, so this is the complete product description column that you're seeing. And along with that, for each and every document or for each and every chunk, we have also added some metadata, which is the price equal to 799. And you can see this is the next product, page content, item name is so and so. And you can scroll all this is a bigger document. This is a company called SLV Works at a price of 2040 at a discount of 0%. No discount is offered here. And you can see metadata ID equal to this is the product ID, and this is the price. The price is equal to 2040. So this is a metadata based search that we are actually doing. Now the question would be, you will probably have a question that what is the relevance of metadata based search? So what is the relevance of metadata based search? Let's see that. Let me explain that to you in a minute, how this will be useful. And this is also technically a concept that is referred to as structured retrieval. This is the reason why metadata based search will be helpful. Because you will obviously have a question, why do we do this? Right? So when we do something, we should first question why we do it. Okay, so why do we need to create the metadata? When we are creating the vector DB, which we are doing in the next step is the same, the embedding model, we create the chroma DB. But now in the database, every chunk is saved with a metadata. So what is the relevance of doing that? What is the relevance of creating a metadata? The relevance is this. We are trying to make our retrievals more efficient. Whatever retrievals we are doing, we are trying to make our retrievals more efficient. This is the more efficient retrieval we are trying to do. Let me explain to you what I mean to say. Okay, let me explain to you what exactly I mean to say by more efficient retrievals. So let's go back to the original question that we asked a while back. So the original question that we had was, remember, I said I want products. I want products costing. I want best battery or best camera products, something like this. Okay, best camera products costing less than 20,000 rupees. This is the user question, right? Now, if this layer was not there, if the filtering layer was not there, imagine I was doing it the normal way. If this was not there, what will happen? Let's say this is not there. Oh, okay. I'm sorry. Let me just remove this part. If this, just ignore this text for a minute. If the normal retrieval was happening, the normal way what we have discussed so far, the vector DB is huge, right? So in the vector DB, you will basically have a million chunks. The vector DB is typically very big. There are 1 million chunks for 1 million products, right? I told you every chunk will become a product description. So, or rather, every product description will become a chunk, and you will have the embeddings for it, right? So when you give a user query, you will have to check and you will have to compare with respect to all the 1 million chunks and find out the top 5 relevant chunks. So you can start to see how computationally expensive this operation will be, right? And I want to also remind you that this entire operation is happening retrieval time. This entire operation is happening retrieval time. So at runtime, when you're basically in the Amazon website, this operation is happening then. So this entire operation is happening retrieval time when you are in the Amazon website. That is the way how it is getting worked out. So this entire operation is happening. This entire operation is happening retrieval time. So you go and query this on the Amazon website. Imagine you're a user and you go to Amazon and you query this on the Amazon website, and this entire operation is happening retrieval time. So the user queries will run very, very slowly. This is the real problem. So what we are discussing right now is a real use case. It's a real problem that we will face, right? It's a very real problem that we will face right now. So because the retrieval is happening, at inference time, it will be very slow. So how can we make it efficient? Instead of going through all the 1 million products, instead of going through all the 1 million chunks and comparing that which is the most relevant chunks, the 5 or 10 most relevant chunks, just to find that information, I don't have to go and search across all the million products. What I can do is, I can do a first layer of filtering first. I will do a first level of filtering. And as part of that, what I will do, I will have a metadata, right? This is what I was mentioning. So when we do the vector DB, we will have a metadata section. We'll have a separate metadata section where we will store the metadata. And remember, for our use case, we have a metadata called price. Okay, so let me write it a bit more in detail. So this is the metadata. So we will have a metadata for price. Here we anyways have the respective product IDs and we have the respective embeddings. Okay, so you have your product IDs, you have your respective descriptions, right? You have your descriptions here. Let me write down the descriptions and the embeddings, right? So your vector DB will be quite detailed. Now every product is a chunk, description is there, embeddings are there, and the price is also there. Let's say this is costing 18,000 rupees. There is another product. We have the description, we have the embeddings, we have the price, which is let's say 22,000 rupees. And we have the description, the embedding, and the price this time is 10,000 rupees. I've only listed out 3 chunks right now for you. Now see what will happen now is, next time a user asks a question, first what we will do is we will first filter the query on the metadata. So we don't have to go through all the million chunks. So first we will do an initial layer of filtering. This is a structured retrieval. So first it is just like running a SQL query and saying select star from the database where the price is less than 20,000, right? So select statements are quite fast comparatively than a, okay, we're simply querying based on the price, which is a lot faster. than searching based on the embeddings. Embedding search is much more computationally expensive. Because remember, each of those vectors are 1024 numbers. The embedding vectors are very long. So if you search based on that, it's very time consuming. But just running a small select query, first checking based on the cost. So here you know that the user is asking something about the price. So first you say, okay, out of the million chunks, there are, let's say, 100 chunks where the price where the price condition is satisfied. I'm just trying to keep it simple. Where the price condition is satisfied. Okay, so out of all the 100 chunks, out of the million chunks, there are only 100 chunks where the price condition is satisfied. So there are only 100 chunks where the entire price condition is satisfied. So now when you do the retrieval will happen, the actual retrieval will happen based on those 100 chunks. Because you don't have to go through this, let's say 22,000. So when you do the retrieval, let's say in this case, the 18,000 chunk will be returned. So now you will search based on the 18,000 and the 22,000 chunk. This is your subset. And now out of these two, you see, okay, where the camera quality is the best, something like that. Okay. So that is what we refer to as structured retrieval. So the LLM is used to create the filter metadata values based on the user query. So based on whatever the user is querying, you try to uh, figure out what the metadata corresponds to. We have a price column. So is the user talking about price? Yes, the user is talking about price. So price 20,000. So first you filter based on price less than 20,000. This filter is then used to refine the documents retrieved from the database. So now you don't have to go and search out of 1 million chunks, which ones are the most relevant. Now you can only search based on the top 100 chunks, which ones are the most relevant. So it's a lot more efficient. So these are small ways how you can really improve the efficiency, or rather the performance of your RAG application. Mind you, it's not about accuracy. This is just about the performance. Because otherwise, performance bottlenecks will happen. A user runs a query and it takes forever to respond. They have to wait for 5 minutes for the answer to come. That is frustrating, right? So these are all, this is a very popular way how you can improve the latency of the RAG application. And that is exactly what I've demonstrated in my notebook. If you see all the way down, I created the embedding model, VectorDB, and this is how your kind of solutions will look like. So if I say good smelling perfume with strong odor, right? So this is what the future of search looks like. So users can go to any e-commerce platform and they can just search like that. You try to do it today using the normal platforms we have, let's say Big Basket and all that. This will not work. They have not integrated this yet because it's costly, right? I mean, who wants to do all this work generally? Things are running fine the normal way, right? And so, I mean, but then maybe in the next few years, this kind of capabilities will become more common. Okay. So a good smelling perfume with strong odor. People can just search like this and the model will retrieve the relevant chunks. You can see it actually retrieve those relevant chunks, or basically those relevant products where these things are there. Scroll all the way to the right and it tells you what those perfumes are. It gives you those chunks and basically displays those products on the page. So that's the use case that I wanted to highlight here. So this example. Now what I want to do over the course of the discussion, I want to also take you through a few other advanced retrieval techniques. We talked about the first one. The first retrieval technique will help you in making the entire RAG process much more efficient. It will become a lot faster. The RAGs will be able to retrieve the results a lot faster. The second approach we use is something called hypothetical questions. What is hypothetical questions is, this also happens right during the vector DB creation phase. Okay, this happens right during the vector DB creation phase. And what we do here is, first part is again, we take the documents, we create the chunks, and then each document chunk is sent to the LLM to generate 5 questions that might be answered by the chunk. This is the additional part that we do. So we take the document, we divide the document into the relevant chunks, 5 chunks. Sorry, not 5 chunks. We take the document and then we create whatever, 1,000 chunks, 10,000 chunks, whatever. So we do the chunking. And then for each and every chunk, we pass it through the large language model and we generate 5 questions per chunk, or k questions per chunk. And these questions are generated in a manner so that the language model, so that they might be answered by the chunk. And now they are stored in the database. the questions and those corresponding chunks are stored in the database. So if you want to see how at a very high level, how the vector database will look like here, this is once again happening right at the vector DB creation phase. If you think how the vector DB will look like right now, the vector DB will look somewhat like this. So every single row will be a chunk. So you will have your document ID, chunk ID, you will have your chunk, whatever chunk it will be, text chunk, image chunk, whatever. And then here you will have your chunk embeddings. And in additionally, you will also have your questions. I'm just discussing at a very high level. You'll have your question 1, question 2. So all the questions will be also stored. Okay, so the questions and chunks are embedded in the and stored in the database. So against every chunk, what are the corresponding questions that this chunk can answer? That is what we are storing. Okay, see this one, all of you. So we have the chunk, we have the chunks embeddings. Let's say the chunk is a page. We have a page, and we are also having 5 questions per page, which that page can answer. So you have a 100-page document. You are dividing the document into, let's say, 100 chunks, because one chunk is one page. Let's say this is 100 chunks. Trying to keep a simple example. So we are saying that one chunk is one chunk per page. So we have 100 chunks. And now we take each and every chunk and create 5 questions. So we take each and every page, pass it through the LLM, and we ask the large language model to tell me that, hey, given that page, please tell me what are the 5 questions that can be answered from that page. So given a particular page of a document, tell me what are the 5 questions you can answer from that page. And now you're storing the page, and you're also storing the 5 questions that could potentially be answered from the page. And now what will happen, this entire thing is happening right during the vector DB creation phase. Now when the user asks a question, this is the RAG, this is the actual retrieval workflow. So now when the end user goes and asks a question, this is the user query. So it will hit the vector DB, the normal retrieval process will happen. Now what will happen is the user question will be compared with these questions. So this will make your retrieval, yes, it is a little bit more computationally expensive. So computationally, it will take a little bit more time, but this will actually increase the accuracy of your RAG applications. The speed will be impacted because the processing is more, but this will improve the accuracy of your RAG applications because you have already pre-processed. So during the time you build the vector DB, you already mentioned what kind of questions could potentially be solved for each page or for each chunk. It is like creating an index. It will kind of speed up, but the initial creation part will be a little slower. It is like creating an index. So next time when the user asks a question, the user will not just go to the chunks and try to figure out which are the relevant chunks, but the user will go to the questions, the question embeddings, and now all that you're saying is you're saying, hey, the user question, we will retrieve those chunks where the user question is most similar to the chunk questions. Okay, so that's the way how we will approach it now. So it will be a little bit more accurate approach. So let's say you are asking the question, hey, what is the pricing of ChatGPT or GPT 3.5 model? If you ask that question, what is the pricing of GPT 3.5 model? We will retrieve those chunks where similar questions have been already stored in the vector DB. That's the way how hypothetical questions approach actually works out. There is something very similar called query expansion. Query expansion basically means that you take the initial user query and you create multiple variations of it with different phrasings. This is again it's very, very useful in scenarios where user queries are unclear. Because see, when end users is very similar to that rephrase response thing that we talked about. The idea is something very similar to that. Because end users are not always very good at writing the best kind of queries. So what we do in query expansion is take the original user query and use a large language model to generate multiple expansions out of it. Multiple variations of the query. Okay, next up, we have something called information compression. This happens right at the retrieval phase. Okay, so this happens right at the retrieval phase. At the top part of the demo, you can see we have discussed the retriever part. So where the user asks a question, the retriever retrieves the relevant chunks. But oftentimes when those chunks are retrieved, sometimes not all the chunks are relevant, right? Think about it. When you go and ask so when we did that exercise, what is the annual revenue of Tesla? The answer to that question was only present in some portions of the chunk, right? So the retriever was used to retrieve the top 5 relevant chunks. That was the general approach that we followed, right? So user asked a question and we are trying to retrieve the top 5 relevant chunks. That's the way we went about it. So user asked a question and we are trying to retrieve the top 5 relevant chunks. What are the top 5 relevant chunks based on the user question? So find out the top 5 relevant chunks, but think about it. The actual answer to the question is only present in some portions. So all the 5 chunks are not needed to answer the question, right? So the actual annual revenue number is only present in one part. It is not present in all the sections, right? Think about it that way. The actual annual revenue is only present in a small section of the document. It is not present in the entire document, right? So the idea here is that we use another compression algorithm to remove irrelevant portions of the retrieved document chunks. And we compress the chunks. So you take the user query, you retrieve the top 5 relevant chunks, but what we are saying is that all the 5 chunks may not be that important. All of those 5 chunks may not be that relevant. So you use one more compression algorithm to, this is another language model you can think of. So what we do is we use another LLM to take those retrieved chunks and we extract the compressed chunks. Think of it as another GPT model where you're saying, hey, this is what I retrieved. So now this is the original question the user asked. So can you take those 5 chunks and can you summarize those 5 chunks for me? It's kind of a summarization. Think of it that way. And another variant of information compression is what we call re-ranking. Again, these are very useful strategies when the relevance scores are low. Relevance scores basically means, something where, so relevance scores basically means something where you are asking a question and the model is not answering it. The model is not doing what it's supposed to do. Remember, there are 2 parameters to evaluate RAGs. We have something called roundedness and there's something called relevance. Relevance means that is the LLM, is the RAG application doing what it's supposed to do? You ask it, what is the annual revenue of Tesla? But it's saying the profits are $30,000. Something like that's the relevance is low. So this will actually help you improve the relevance scores because you're getting better chunks. If you're retrieving the right information, then the relevance scores will be better. So one way to do it is to do information compression. So get all those chunks and then compress those chunks only to get the most relevant ones. Another way to do it is using re-ranking. Re-ranking is a similar approach. What we do is we extract the top 5 relevant chunks, the normal approach, and then we re-rank and then we rank them based on the ones which are most relevant. So we don't outright summarize or compress, but what we do is we re-rank it. It's kind of a weightage that we assign. The idea is very, very similar. Both can be used. And putting it all together, this is just one approach where we kind of put all the things in one place. So all these strategies have been discussed here. You can see. Okay, so this is what will happen during the vector DB creation phase. And here we talked about something called structured retrieval. So you have the metadata put in. So metadata based search should be enabled. We also discussed about something called hypothetical questions. So while creating the vector DB, have hypothetical questions and also store the embeddings for all those hypothetical questions. So that is the other part that we talked about. This is the normal chunking part. All that you do, store the chunks. And then at the retrieval time, we talked about optimization. What is optimization? We talked about information compression and we talked about re-ranking. So while retrieving the relevant chunks, so yes, all the chunks may not have the complete information. So you take the top 5 chunks or top 10 chunks, and from that you do compression or re-ranking. So get the most optimized chunks, and that send it to the LLM model. Get the API call, do the API call, get the response. pass it through a content filter. This is guardrails. Guardrails are basically additional layer of filtering that they are doing. This is that content safety part that we talked about, right? And then give the final output. And this is the another part that we talked about was query expansion. So the end user, when they are writing a query, so that hits the UI, and from the UI, it is actually like it is actually doing query expansion. So the end users are not the best at writing the query. Okay, so the end user sometimes they may not write the best quality of the queries. So we do another layer of query expansion. So the user query is taken, and we generate many variations of the user query, and we feed it to the LLM. So this is how the different types of advanced retrieval techniques can be used. Okay, and all of these are they're fairly advanced ideas, they're fairly new ideas, but all of this will ensure that you're able to create high quality RAG applications. Okay, so we can create high quality RAG applications using these concepts. And the demo of all of these things, the demo of all of these things is highlighted here. If you go back to that particular multimodal research assistant, so this is where I have highlighted, I've demoed all these ideas. Okay, so all of these ideas are beautifully demoed in this particular thing. So if you can go through it, you can go through query expansion, you can see hypothetical questions, you will see re-ranking, you will see information compression, and you will see structured retrieval. So all the 5 core ideas, the 5 most widely used RAG techniques, improvement techniques have been highlighted in this demo. Okay, so this is the way how you can approach it. So I've also given a LlamaParse demo here, and you will see there's a LlamaParse demo that I've also given somewhere here. So there's a small demonstration of LlamaParse I've also done here for all of you, right? So just to clarify, in case you want to go over LlamaParse, there's another small demo that I've also provided here on LlamaParse. So that's about RAGs. A lot of RAGs we talked about. There are a couple of other exercises we can also do on RAGs. So, but this is pretty much what we have with respect to retrieval augmented generation. And now we will be coming to another very interesting topic called agents. That is the next part of our conversation. It's an extension of RAGs. And as I told you right at the beginning of the session, is this will easily take care of like whatever we have covered until now. Until now, whatever we have talked about, this easily covers close to 90% of all your use cases. And now we will discuss the next 10%, which is agents and deployment. So we will discuss that part in the next phase of our session. That is what is pending. Very exciting topic. So agents are not something very different. So when we talk about agents, we will discuss the concept of agents. We will discuss some basic applications of agents, and we will completely use something called LangChain. So in this part of the discussion, we will totally use LangChain to build agents. So 2 approaches we will follow. One, we will use predefined frameworks like LangChain. And second, we will also look at other approaches. We will also look at end-to-end agents that we can build manually. So in this part of the discussion, we'll actually look at some end-to-end agents and also deploy it. So this is what we'll talk about. We'll introduce agents. We'll talk about what agents are. We will introduce a very popular paradigm for building agents called React. Now, there are a lot of other paradigms that exist. There are a lot of other paradigms. Reflection is a paradigm. So we will start off with agents, and this is the basic concept we will cover. And I'll give you enough ideas in terms of how to design agents using other paradigms also. And we will also see an end-to-end use case. It will be a very demo-heavy session. 5 to 10 minutes of slides we will talk about, concepts we will talk about, and then rest of it, the next 1 hour will be all agentic, very interesting agentic demos we will see. So that's the plan of action. So what I wanted to start out is a very practical application. All of you can see on the screen. It's a very practical application that I'm sure each one of you in the audience can relate to. How in the real world you will have a database, right? Let's say you have a database. You have a database which consists of customer information, and you want to write a query. You want to write a query and get an answer. This is the exact same question some of you are asking me yesterday, that Sayan, I have a similar use case where I have a database where I have a lot of tables and a lot of data about customers and transactions and orders and whatnot. And what you want to do is you want to go and query from the database in natural language, and you want to get an answer in natural language. Natural language could be anything. Now here we are talking about English, but it can be any language. So this is the end result, or the end result of what we are trying to achieve. One of the results. There are a lot of other things we will be seeing, but one of the applications of agents is doing something like this end to end. If you see what we have done so far, what we have worked on so far, the large language models, they are not thinking engines. The LLMs are, they are language models where you give them some input prompt and they will generate a response based on whatever input prompt you're providing. And which is where we spend a lot of time in curating the prompt, fine tuning the prompt. We have to write a very detailed system message. We have to write a very detailed user message. We spend a lot of time discussing those pieces. But one very important aspect of the large language models is they will not do everything end to end, right? If you want to build a complete application, the complete application is not just text generation. The complete application is not just classification. There are lots of moving pieces in the application, right? So think of agents as an automated way of doing all of those things. So large language models are only text in, text out systems. You give it some input text and they will generate some output response, but they will not take actions on your behalf. They will not think and do something for you. Now, agents are a complete package. What is powering them are large language models. There are LLMs that are powering them. LLMs are the brain behind it, which we'll see. But they are the complete package. And let's see what I mean to say by that. So in a very simple way, an agent is nothing but LLM plus tools. Now, as I told you, the large language model is the brain. This is the processor. So you can think of it like the manager. So the analogy that I like to take here is this is the manager. So the LLM is like the manager. So the LLM is like the manager. And the manager is a very, very well-trained and very powerful manager. So the manager has a lot of knowledge about different things. But the manager cannot do everything by himself or herself, right? The manager needs a team. They need a team of developers, architects, testers to get things done, right? So think of the large language model, the GPT-4 Omni model as a kind of a manager. The manager itself cannot do everything, right? So the manager will need access to tools. So tools are the workers. So tools are the workers which will be used to get the things done for the manager. So the workers will work in tandem to get things done for the managers. So the tools are the workers. And these are the example tools that I've listed out for you. Search engine, Python runtime, database. So what it means is that you are giving the large language model ability to connect to a search engine like Google search, Yahoo, whatever. Okay. You are giving the ability to the large language model to connect to a Python runtime to run some Python code. Okay, so you write some Python query and the large language model will be able to run it for you. You give it access to connect to a Python runtime, and then you also give it access to connect to a database. So you give it connectivity to some kind of backend SQL Server database or Oracle database, whatever. It could be a SQLite database. Okay, there can be other kinds of tools also. You can have a tool where you allow the large language model to connect to Yahoo Finance API or some weather API. Okay, some kind of weather API to get the live weather data. Okay, another example of tool could be you connect it to the Yahoo Finance API. This is the one that we will use in the live end-to-end demo today. So we will actually use a large language model to connect to the Yahoo Finance API to get the live stock information. Another example could be you want to use a large language model to connect to the news API to get real-time news information. These are example workers. So the large language model, the GPT-4 Omni model itself cannot do everything. Because remember, very, very important, the GPT-4 Omni model was trained latest as of 2023. Okay, it was released in 2024, but the knowledge cutoff was 2023. Okay, so it only has data latest as of 2023. So it will not have access to real-time information. If you ask it some questions, the GPT-4o model will not be able to give you answers to those questions. It will not be able to give you the real-time information. The real-time answers will not come out. And that is an important thing to keep in mind. So then how can you augment the ability of the large language model? So the manager itself is quite good, but the manager will not be able to do everything. The manager doesn't have latest information. So the manager will need the help of workers. So there is worker one that will connect to the search engine, worker two that will connect to the Python runtime, Like this, there can be hundreds and thousands and tens of thousands of workers that can be connected. And if the manager wants to get something done, the manager will have enough intelligence to know, given a task, which worker to ask, which worker to call, or in other words, which tool to call. We call it a tool calling agent actually. The tool calling is another kind of agentic paradigm. So all that the LLM is trying to do is, given a user query, so you can see here the user asks a question, how many customers have subscribed to the term deposit? Given the question, given the user message, the LLM will be a normal LLM, right? You have a user query, user message. LLM will have its own system message, prompt parameters, all this is standard stuff. Now the LLM will have an inherent ability to understand, based on the user question, what tool to call. I have access to thousands of tools. I have thousands of tools at my disposal. So now I can decide which tool to call. Out of all the thousands of tools, I can decide which tool to call to solve the problem. And that's the way how you think of an agent. So it will call them in a sequence. Or let's say, first to answer this question, the LLM understands, okay, this is the question. This is something to do with customer, something to do with term deposit and all that. So to answer this question, I need to connect to a database runtime. So the answer to the question will not come from Yahoo Finance or weather or news. So the language model should have enough understanding of that. That which workers I need to connect to answer this question. That is the first part. Once you figure that out, you call that relevant tool. Okay, in this case, you see what we did. We went to the database runtime. It actually identified the SQL query. What is the SQL query? It composed that. The query was run. The output was presented in natural language. So this entire set of things were happening, and the large language model was controlling the entire execution. Now this is a very simple use case, but agentic systems can be a lot more complex. Now in this case, we used only a single worker. We only used the database tool. But in reality, you can have an agent which uses multiple tools simultaneously. So it could be that you are using some database tool, and after the output comes from the database tool, you will have to call a Python runtime. So you need the results of a SQL query and also a corresponding Python command. Both has to be executed together for the final outcome to be generated. So in that case, the language model should take the call that, okay, given the user query, let's say I ask this question, how many customers subscribe to the term deposit, and like whatever, what is my latest stock price of Apple, something like that. Okay, you want to find some correlation between customers subscribing to term deposit and latest stock price of Apple. So the moment you ask that kind of a question, the language model will understand that to solve that problem, I need to connect to a database runtime, and I also need to get the latest Apple stock price from the Yahoo Finance API. So both these workers will be triggered. Both these tools will be called. Tool calling is what we will do. We will get the answer, and the LLM will present the final answer. So you can see the ideas are very similar. The ideas of agents are very similar. It's an extension of everything that we have talked about, right? So they're doing some kind of a retrieval and all that. Okay, and it's just a complete end-to-end package. Okay, and the reason why agents are like such a big topic and such a big exciting area today is because they are as close as we have ever gotten to a truly intelligent agent, truly intelligent AI system, right? Because historically, we had that beautiful introduction we discussed on the first day, right? AI, rule-based intelligence, expert systems, how we evolved from there, how we evolved from expert systems to machine learning, deep learning, and now we have generative AI. And specifically within generative AI, agents are a very, very exciting topic. And the reason is because they are really intelligent. They are as close as we have come to true general artificial intelligence. Okay, so this is why it's so powerful, because you can literally have them do everything. You can literally have a agent do everything. So you can connect to multiple tools and it will do everything for you. Okay, and just to connect the conversation a little better, with some of the things we have discussed in the session so far. If you remember, we talked about ChatGPT. We talked about a lot of other things. So these are all agentic systems. So next time you log into a ChatGPT and you write a query, what you're actually doing is you're calling an agent. See, this is by default a GPT-4 model, right? So if I go and ask the question, what is the latest news? What is it doing behind the scenes? Think about it. Behind the scenes, there is a GPT model that is running. If you go and ask the same question to your Azure portal, Azure GPT-4 Omni model, it will not be able to give you the answer because that's just a language model. But the moment you browse it through chatgpt.com, this is actually an agentic system. This is not just a language model. What you are browsing right now is an agent. This is an agent that is connected to multiple other moving pieces behind the scenes. So behind the scenes, this is connected to many other extensions are there and all that. So unfortunately, I don't have the GPT Plus to show you. But if you have the GPT Plus subscription, you could actually you actually have an option to connect to multiple other explore GPTs and all that you can do, right? So you have an option to go to explore GPTs, and there you can actually see a whole lot of other things, right? So if you go to explore GPTs, you'll be able to kind of see a whole lot of other options. So I just wanted to show you briefly what Explore GPTs I was talking about. You see a lot of Explore GPTs are there. So can you see we have got specific GPTs that are like if I go to productivity or lifestyle, I found there was something from Expedia actually. So if you can actually search for Expedia. So turns out Expedia there is a particular GPT for that. So what are these things? These are all extensions. So the moment you are browsing chatgpt.com, you are basically trying to access you are basically trying to use the underlying language model, which is GPT-4 Omni or whatever model that you choose to use. Okay, if you have the Plus subscription, you have more models available. And then at the back end, when you ask a question, the agent will decide what tool to call to answer that question. So in this case, I can ask a query saying, "Hey, get me the top flights from India to Dubai in the next 7 days." So my LLM will understand that to answer that question, I will have to connect to the Expedia API. So all these integrations are done behind the scenes, and that's what makes agents so powerful, right? I can show you. And Gemini is also a very, very powerful agent actually. So when you go to Gemini, it's also an excellent example of what we refer to as an agent. Okay, so there you actually have extensions, and what you can do is you can go to the extension section, and you can effectively go and you can enable Gemini to connect to all your stuff. So that's one of the ways how you can also work it out. Okay, so for example, I can take you to my Gemini. So this is my Gemini. All of you can see. This is my personal Gemini account, and so you can normally write your queries and all that, right? And what you can do is so you can actually go and go to settings, and you can go to apps, and once you go to apps, you can actually give Gemini access to all these things. And they've recently added GitHub. This is a very new inclusion. This was maybe hardly a few weeks old, maybe 1 week, very recent. So Gemini actually allows you to even connect to GitHub. How cool is that? How cool is that? You can actually, like, you can write a query, and Gemini will be able to retrieve the information from GitHub. So this is an agent. So whenever you access these models through these websites, what you're actually using is an agentic system. So this is a language model, and that language model has integrations, and through other extensions, it is able to call different tools. Like in this case, see Google Workspace. So if I ask it a question, Google will be able to. If I ask it a question, Google will be able to figure out, based on the question, Google will be able to figure out what tool to use to answer that question. So I can actually try out a query which says, okay, show me the top 5 finance emails. And if I do that, it will actually show me all my top emails from Gmail. It it will figure out of all the tools that are available, which tool to call. You can ask it questions with respect to Drive, questions with respect to Notes. Google Keep is for Google Notes, right? So the integration is very, very good. Even Google Flights, even YouTube for that matter. You can look it up. You can find out the top videos, what kind of videos you have watched. It's very personalized to your account. So what you're seeing here is again a true agent in a way. Okay, so it's quite exciting. Like some of the things that are possible, and potentially some of the things that can be done with agentic systems. Okay, now let's get a little deeper into how do we design agents. What is the React paradigm? React is one of the paradigms that we will use generally. And this React is not your React framework. Okay, this is not your front end, it's not your web development, React.js, not that. So this is React, which stands for reason and act. Okay, so React stands for reason and act. This is a specific paradigm that we use for building agentic systems. So React is a specific paradigm that we use for designing agentic systems. That's a React paradigm that we use. Okay, and what are the different components of the React paradigm? So thought, action, observation. Okay, so React means reason and act. It's quite obvious, right? So first you think what you want to do, first reason. So you're given a problem. How do you solve a problem? First you think. First you think how you will solve the problem, and then you act. There are two steps to the whole puzzle, right? So first you reason, first you think what you want to do, how you will approach it. First you think, and then you act. So the React paradigm is completely based on that. So first you think what you want to do, and then you act on the basis of that. That's a React. And this is based on these thought action observation chains. Okay, so first you think what it is, what is the current state, what is the problem you are required to solve, what are the different options you have, how do you go about it. First you think, put some thought, then you act, then you take the action. Taking the action means you decide what tool to call. Like when I ask the question, what is the query and how many customers will subscribe to my term deposit? You first look at my question, first look at the query, and then you figure out what tool do I need to call to answer that question. What tool do I need to call? That's the way we go about it. So you decide an action, and then after you decide the action, you do an observation. You observe and you see what are the different aspects. So that's the way how we go about it. So thought, action, observation chain. So think, act, observe. Think, act, observe. Think, act, observe. Okay, and get the final solution. That's how we go about it. That's how we go about it. Now, what I will do now, now we see a small hands-on with respect to how this is done. And before that, I also wanted to show you a couple of beautiful animations to help us understand and solidify this concept a little better. It's always best way to learn things visually, right? So I'll show you a couple of very nice visual depictions in terms of how this is actually working. So let us see that. So there is this wonderful website called explainedprompt.com. Okay, this is a wonderful website which actually explains all the different types of prompting techniques. And I wanted to explain the idea of an agent through this particular site. And you can actually see a lot of the topics that we have already discussed. Like you can see zero-shot learning. So I talked about it. What is zero-shot prompting, right? So language models are zero-shot learners. You can see chain of thought prompting, how it happens. So language models are few-shot learners. This is also a beautiful demonstration where they actually show you that compared to zero-shot prompting, even if you give a few examples, even if you give it 2 to 3 examples, the performance of your language models will improve drastically. So this is a very nice visual way how the whole thing has been depicted. What we are interested in right now is this part, React. This is the agentic part we are discussing. But as I told you, there are different paradigms. There's something called reflection. There's something called tool calling. So multiple ways we can do it, but we will focus on React for the time being. So this is where the React framework is designed, has been explained very, very beautifully, right? So you can give it a read what it's talking about right now. This paper introduces React, a novel approach that combines reasoning and tool use in language models. Tool use, remember. So tools are the most important component of an agent. Okay, because underlying the manager is the large language model, the LLM. LLM is the one who has a thinking capability. That's the manager. Manager is the one who will juggle the resources. But what are the resources? Who will do the work? Who are the actual workers? The workers are the tools. So tools are the absolute, the most important component of an agent. Okay, so by interleave reasoning traces and actions, React is able to perform dynamic reasoning. Okay, so you can actually just this whole lot of text is there. So now let's come to the actual use case. Okay, so let us see how the React framework is working. Aside from the Apple remote, what other devices can control the program? App remote can control the program. App remote was originally designed to interact with. Okay, so this is a sample question from the hotspot QA dataset, which was used to evaluate the React prompting on question answering tasks. Okay, because ultimately I told you evaluation is very, very important. So there are a lot of benchmarks that are used for evaluation. So whenever any new language model is developed, a lot of these benchmarks datasets are used for evaluating the performance of these language models. So we have taken one of these benchmark datasets called the hotspot QA dataset. You can actually see if you want to. You can actually go and look it up what kind of dataset it is. So these are actually very, very popular benchmarks that are there. Okay, and a lot of the top models are usually tested on these benchmarks. Okay, this is just one example I'm showing you what benchmarks mean. Anyway, so this is the question that is asked. Now, what is the next step? Let's see. Next step. So solve a question. Uh, so this is the prompt that you will typically give, right? So the prompt starts with instructions for the model to follow thought, action, observation cycle of React prompting, followed by a list of available tools. Okay, so remember React is based on reason and act, and it is primarily the idea is thought, action, observation. You first think, then you act, then you observe what happened and what is the next step I have to take. It's a cycle, it's a chain. It's keep going on and on and on until the end happens. So that's the way how the thought action observation chain will work out. So you will to write a very detailed prompt. So let's say we write a prompt, and based on the prompt, you start with instructions. So you see, solve a question answering task, it interleaving thought action observation steps. So thought can reason about the current situation, and action can be of the three types. So you're writing a very detailed prompt. You're specifying that, okay, what is the meaning of a thought? Thought is the part where you reason, you think what is to be done. This is the prompt. This is the system message, by the way. And action can be of the three types. So you explicitly specify what action the LLM can take, what action the agent can take. Okay, and what are the actions? First, you give it access to a search tool, and you specify what is the search tool going to do. Then you give it access to a lookup tool, and you specify what is the lookup tool going to do. And then you give it access to a finish tool. So this entire thing should be part of the system message prompt. Okay, each tool definition shows how to call the tool and describes what the tool should be supposed to do. This is how the model decides which tool to use to answer the question. Okay, so when we define these tools later on in the demo, I'll show you how to design, how to create these tools. It's very important, and these are actually Python functions. So when we come to the demo later, we will see that these tools are nothing but Python functions. Okay, so if you have a search tool, you will create a Python function for search, and you will also give a doc string for that function, which specifies what that function is supposed to do. It has to be a very well commented function, and the description of that function should specify very clearly what that function is supposed to do. The function should be described very appropriately. The lookup tool is the one that will return the next sentence containing the keyword, and the finish tool will return the answer. So you say, okay, this is what I'm supposed to do. Given the question, think how to proceed, and then act by using any one of the tools. Okay, that's the way. Let's look at one example. Let's look at one example how this will work out. Okay, this is one example, and complete end-to-end example we are seeing. What is the elevation range for the area that the eastern sector of Colorado extends into? Right. So this is the question that is asked. User message. So what will happen? Now this will be given to the agent, and the agent will start working. Remember, agent is LLM plus tools. So what is the prompt that is written behind the scenes? So first the agent has to think, okay? Or rather the LLM has to think. When I say agent, I mean LLM. Okay, that is the brain of the system, right? I need to search the Colorado orogeny, find the area that the eastern sector of the Colorado orogeny extends into, then find the elevation range of the area. This is what it is supposed to do, right? This is the entire plan of action that has been created. Now let's see. Let's go to the next step. Okay, so you can actually, you can actually go step by step if you want to do this along with me. Let's see. So search for Colorado orogeny. Okay, where will we search? We will go to Wikipedia and do a search. Right, so we can search for Colorado orogeny. Let me show you on Wikipedia how this looks like. Actually, it's a great way to learn. It's a very visual way to learn how it's actually happening. You can see. See if I can show you in the same interface. See. So I'm searching for Colorado orogeny. I'm just showing you in the same window. And when I search, you can see. Look at the first line is written. This is exactly what we are seeing on the screen, right? All of you can see. The Colorado orogeny was an episode of mountain building in Colorado and surrounding areas. Can you see? This is exactly what we are seeing on Wikipedia. So when we search, we are able to return the first text. So thought, it acted, it used the search tool, it tried to find out about Colorado orogeny, and then it observed, okay, this is what was returned. Then the agent is thinking again that, hey, this is returned, which is fine, but it does not mention about the eastern sector. So I need to look up the eastern sector, right? Now, what is the eastern sector? How do you look it up? So what I can do is I can do a control F. It's quite literally how it is, okay? And it is searching for the eastern sector. Okay, so it is actually, you can actually search for the eastern sector. And when you do that, you can see, look at this part. The eastern sector extends into the high plains, and it is called Central Plains orogeny. Can you see? This is exactly the text that is written here. The eastern sector extends into the high plains, and it is called Central Plains orogeny. All good. We return this, we return this. Again, the agent is thinking, okay, the eastern sector extends into the high plains. So I need to now search high plains and find its elevation range. So see how it is methodically figuring it out. And now what I will do, I will simply search for high plains and find out its elevation range. Okay, so I go and search this out. See, when I search for high plains, I'm not exactly getting the complete information. So rather, I need to search for High Plains, United States. Okay, so now you need to go and use a new search tool, not lookup. Lookup basically means that you're looking up in the same document. So now it figures out that I need to instead search for High Plains, United States. So go and search for this now. I will go and search for this now. This is going to be a new Wikipedia search I will have to do. So when I go and search for High Plains, United States, I will actually get the complete answer. The first, yeah, I will get the complete answer. Okay, and I will get the complete answer in terms of elevation. So that's the way how the entire thing will basically work out. If you see when I search for High Plains, United States, the complete elevation will come from here. Can you see? Look at the numbers are coming. See 1500 to 600. All this is coming up right now. So see how the methodical way how we went about it. So thought, action, observation. So first you ask the question, user message, agent thinks what to do, then it decides what tool to call to solve the problem, action, then observes again acts, observe. So that thought, action, observation is continuing to go on and on and on until it stops. So that's the way how we go about it. And this is what is achieved using what we call a React prompt. So there's a specific type of prompt that we write called a React prompt. And we will see that in the demo right now, how these kinds of prompts are written and how we actually build a agentic system. So we will start off with a very basic demo. We will start off with a very, very basic demo, how an agent is created, and then we will see some more advanced end-to-end demonstrations of agentic systems. So let us see a very basic demo of how to create an agent. So all of you can see the screen, and we are using the LangChain library for doing this task. Initial part is all the same, API keys, Azure API keys, all that we already did. Here is a bit of text I've given you to explain the framework again. And see this part. This is exactly what I was explaining. See, I just tried to explain you two different types of tools. One is a Python tool, and one is basically a DuckDuckGo search tool. Okay, so these are the Python, the tools that we are able to see. You know, this is very interesting. Actually, a couple of days back, when we started the session a few days, 2 days back, remember I told you OpenAI has signed an agreement with Windsurf. Windsurf is actually a coding platform, right? So just like Cursor, Windsurf is also like a coding engine, right? And a lot of companies are actually trying to come up with these kind of integrations. If you think about it, if you think about another very, very practical example of agents, let me show you. You can actually run code inside ChatGPT, you know. So if you go to ChatGPT, you can actually run code inside it. So I can literally say, you know, I can literally say build a classification model. I'm just taking a basic machine learning task, okay? So build a classification model. So I'm taking a simple classification task right now. Yeah, this might be a little technical, or maybe I can take a more generic task which everybody can understand. So write a program to write a program to add two numbers. I don't think there's any rocket science about this very, very basic thing, right? So write a function to add two numbers. Generate the code and allow me to test it. Test a function by calling it. I know I'm making it too advanced right now, but you can see that you can literally do this with very little supervision also. But anyways, I can run this, and what it will do is what the GPT model will do is it can go and it can go and literally generate the code for me. Not only that, not only that, it even has the ability. It even has the ability to call to call this, right? It even has the ability to run this at the back end. Now, not all the time. It's again limited by there are some restrictions. If you have a very complex thing, it may not run, but it does have the ability to even use a Python runtime behind the scenes. So that's one of the ways to basically work it out, how this is working behind the scenes. Okay, so if I say run the program, if I just say run the program, okay, so whatever program I wrote, see, look at this. Did you see how it ran it? This is where the the overall the Python runtime is actually getting used. Okay, so this is the Python runtime that is used behind the scenes. So remember, the language model is GPT-4 Omni, but ChatGPT.com is an agent. So it is a language model, but it is also connected to a Python runtime. So I can write any query, and it will send it back into a Python runtime engine, and that is what is executing the code. But this capability everybody will not have. Like, if I, for example, at least last I checked, Gemini did not have the capability. I'm not sure if they have recently modified it or whatever. We need to check that. But if you take a look at it, Gemini inherently doesn't have the capability to run the code. Okay, so it will generate the code nicely for you. See, here I'm able to very nicely generate the code. Very detailed, right? Gemini is very detailed in terms of how by if I ask a question, Gemini is it's a very large context window, I told you. So that's why usually the outputs in Gemini will be a lot bigger. See, it does a lot more. Simple question I'm asking, but it tells me so much. The output tokens are huge, right? And you can see now I can go and if I say run the code, run the program. If I say run the program, uh, look at this. Can you see? Can you see? I cannot directly run a program in the same way you could on your computer. So these are some of the limitations you need to be aware of, right? So again, I mean, Gemini is great, huge context window, but in terms of coding tasks, it will write code better. It will write code in a very good way, but it will not inherently run the code for you because it is not connected to the backend to a Python runtime. Okay, so these are again things to be aware of. These are all agents what you're seeing on the screen. So whenever you access Gemini.google.com, it's an agent. So it's not connected to a backend Python runtime the same way that maybe a chat GPT is connected to. It actually ran it successfully. You can actually copy paste any code and say run this code and it'll actually run it for you. Although not very advanced stuff, because remember if something, I mean, don't try to copy paste your vector DB creation code, and it will not do that because it needs GPUs and it cannot use GPUs obviously. Okay, so very basic code snippets it will run, but not some advanced snippets and all it will not run. I hope over the course of this discussion, everybody appreciates what agents are in a better way. So this is where I have actually created the tools first. I told you how we use LangChains and the tool classes to create the tools. Okay, so you can see this one in action. So this is the Python REPL. So we instantiate Python REPL, and all of this is defined here. See, from LangChain. So from LangChain, we get Python REPL. From LangChain, we also get DuckDuckGo search and Yahoo Finance. We will use both of these in our demo here, right? So we instantiate the Python REPL, and here we basically wrap this REPL as a tool. And this is the way how we wrap it as a tool. We use a tool class in LangChain. Again, this is a very simple way how we are creating a tool. But if you want to do it a little bit more manually, we will see later on that we can actually create a function. You can create a Python function to do this. But here we simply use the tool class to wrap it as a tool. And if I want to call the tool, I can simply say REPL tool.invoke. This is all code, okay? This is all syntax. Uh, I mean, as long as the concept is clear, what we are talking about from now for the next half an hour will be just syntax. That's it. So don't worry too much about the syntax. Understand the end-to-end application flow because you already have extremely powerful code editors which will do all this heavy lifting work for you. So please don't, get too nervous and confused with the syntax. Okay. Okay. So now this is the same way how I'm instantiating the DuckDuckGo search tool. So I'm instantiating DuckDuckGo search. I'm wrapping it as a tool. So tool name equal to DuckDuckGo search. This is the same name I'm giving. Okay. Whatever name I gave here, same name I'm giving here. Description part is very important because I told you this is the only way that because this is tool is a worker. Okay. How will your manager know what you can do? You will have a manager, right? Your manager will only know what you do based on your resume, based on your interview, based on your skills, whatever. You have to tell that, hey, my name is Sayan, I'm very good in doing this. So that is what how the manager will know, okay, there's somebody called Sayan in my team, and Sayan is very good in GenAI, right? So next time I get any user query on GenAI, I'll give it to Sayan. So for that to happen, the description has to be proper. The description is actually a very, very important thing. You must describe the functions correctly, the tools correctly, sorry. Okay. So by now we have defined two tools. And if I want to test out my search tool, you can see search tool.invoke is the code I use. Very simple. Who is the founder of TestUp? Straightforward. Now, moving on, let us see the complete end-to-end implementation with respect to an agent. What we have done until now, we have defined two tools, right? Let me show you. We have defined two tools. So we have defined the DuckDuckGo search tool. We already talked about it. And we have defined the Yahoo Finance tool. Okay, see the code. So step one, we have defined the DuckDuckGo search tool by wrapping it in the tool class. And step two, we have defined a Yahoo Finance tool by wrapping it in the tool class. Okay, so this is the two tools that I've instantiated. And this is the part where I'm defining the React prompt. Because remember, the entire functioning of the agent is ultimately controlled by a prompt. There is a prompt that is working behind the scenes, right? The entire functioning of the agent is ultimately controlled by a prompt. There is a prompt that is working behind the scenes. And this is where I'm actually using a kind of a React prompt. I'm not defining the React prompt manually. What I'm doing is I'm simply taking it from some open source place. Okay, so this is where I'm pulling it from. Okay, we'll see some demos where we'll even write the prompt manually. I was just trying to quickly look up the prompt where it is. Okay, just a minute. Yeah, this is where it is. Yeah, I've simply just clicked on the link. I just copy pasted the link here. And this is what the React prompt looks like. All of you can see. So I've simply pulled it from here. Can you see? I did hub.pull hwj17 React. So this is the Langsmith hub. And in case you're wondering where is hub defined, so this is where I instantiated all those libraries. Okay, so all this is LangChain import hub. When I say LangChain import hub, I can actually pull all the resources from here. This is how I'm actually pulling this particular resource. Okay, so if you want to use it, you can also use it. So if you just click on try it, if you just click on try it, you can actually try the prompt here. And if you want to use it, it will give you the same query, how you can go back and use it. So this is basically what we did. Can you see? So from Langsmith import client, this is just an alias that I'm defining. Okay, and I'm just saying client.pull, straightforward. Okay, so this is how we can use it in the the Python SDK. Anyway, so this is what the prompt looks like. All of you can see. It looks very simple, plain and simple English is what we have defined here, right? So answer the questions as best as you can. You have access to the following tools. So this is the prompt for the LLM. So the LLM will it has access to these tools. So this is the prompt for the manager. So we are telling the manager in advance that okay, you have access to all these workers. These workers have been very clearly defined, which we have already done that later, and then use the following format. Okay, so question, thought, action, observation, and repeat thought, action, observation n times until you know the final answer. Okay, so this is the way how we do it, and it can be more detailed. I mean, this is a very simple example of a prompt, but it can be more detailed, right? So we do that, and this is how we finally instantiate the agent. Remember, I told you agent is basically LLM plus tools plus prompt. So these are the three main components of an agent. Okay, so there's a language model. There's a language model that we've been talking right from day one, the GPT-4 Omni model or whatever model you want to use. There is a prompt that we just now talked about. There is a React prompt that we have to write where we explicitly specify what framework we want to use. Now here is React, but if you want a different framework, let's say reflection, you will have to write and adjust the prompt accordingly. Okay, and we also specify the list of tools. What are the tools that we have? Okay, and we specify the tools as a list here: search tool and finance tool. Okay, so straightforward. And now we are just running the prompt right now. So sorry, testing the agent right now. What is the latest stock price of AAPL? Okay, so we can just test out the prompt. What is the latest stock price of AAPL? How do we solve that problem? So given a question, what is the latest stock price of AAPL? What we can do, we can go and effectively, first the agent will figure out what tool to use to solve the problem. Okay, so first the agent will decide what tool to use to solve the problem. So it has a list of tools available. One is DuckDuckGo search and one is this thing. So it will first figure out what tool to use to solve the problem. So turns out that it has to first figure out what is AAPL. So first it has to go to Yahoo Finance and it will try to find out what is the corresponding ticker symbol of AAPL. That is the first step. Okay, so what is the corresponding ticker symbol with respect to AAPL? So first find that out. And once we do that, once we find out what is the corresponding ticker symbol for AAPL, which is Apple, then you go to DuckDuckGo search and you get the latest stock price of Apple, which is 189.87. Okay, so that's the way how we do it. All right, so we can see that given this question, this is the original question the user asked, the agent will respond the latest stock price is 189.87. Okay, so but the magic is all happening in the intermediate layers. There can be multiple calls that are happening. There can be multiple external agents or extensions that we have connected this to. Yahoo Finance API, DuckDuckGo Search API, even Google Search, by the way. Google Search is paid. That's why we haven't used it. DuckDuckGo is free. But if you can also use Google Search, but you need to have an API key and all that. Okay, so you can see this one. And if you scroll down, you're just asking one more question. What was TSLA's quarterly revenue from the latest earnings call? And same way, we are first trying to figure out what is the corresponding uh, name of the company with respect to its ticker symbol. So TSLA stands for Tesla. So that's the part that we are able to figure out. from Yahoo Finance News. And once we get that, now we go to DuckDuckGo search and we are able to figure out this thing. Turns out it says the revenue data is not available. Okay, so that's what is found out. All right, so this is how we do this. And the next example that I showed is how to create a data frame agent. Data frame agent is also like this is the same use case that we were talking about. And you can see I took a data frame, a sample data frame in Pandas. So we took a sample data frame called bank data. This is the bank data set. So it consists of customer information with respect to a customer's job, their marital status, education, default status, balance, and all that. And we are trying to do some querying based on that. Okay, so this is the built-in function. We are not having to do this manually. This is a built-in function that LangChain already comes integrated with. LangChain gives you this particular way to, it has a built-in agent that you can directly use on data frames, pandas data frames in Python. Okay, so you can specify the language model, which is GPT-3.5. You can specify your data frame, which is bank data. This is my data frame in Python, and that's it. It'll straight away work. How will it work? Well, you can give some sample inputs. These are some sample input queries that I'm giving. How many customers have defaulted on loans? What is the average balance maintained by a customer? How many customers have subscribed to a term deposit? You can specify some sample inputs here. And once you do that, let me show you the execution. So this is the execution. You can see how many customers will default the next month and see how it is working. So given this question, how many customers will default the next month? I'm sure many of you in this audience who know how to query data frames or Python, you know how to get this right. If I ask the question, how many customers will default the next month? What do you do? What do you do? This is the query, no? df default. So default is my column. So you want to access the column and then do value counts, right? So when you say df default value counts, what you get is basically this. Okay, so from the data frame, you can say value counts, and that will give you all the unique categories, no and yes, and how many of them are there. And from here, the agent is able to figure out that, okay, there are 168 customers who have defaulted, or maybe let's say who will default. Okay, so you can see to determine the number of customers who will default next month, we need to analyze the default column of the data frame. So this is the intelligence of my language model. So that's the way how we are actually going about it. Okay, and this is also very interesting. See, however, based on the provided data, it seems that a default column indicates the current default status of the customers and not a prediction for the next month. It even has the intelligence to figure that out. Okay, so see, it is so detailed actually. Okay, so the agent is just working on the data frame. So based on your question in natural language, we are able to generate the result in English. Okay, so we don't have to write the code in a way. So next time you have any problem, you have any table in a data frame, any data available in a data frame in Python, you can literally ask something in natural language, and the entire exploratory analysis will happen automatically behind the scenes. Okay, so I have a slightly more exhaustive notebook where I've kind of walked you through this a bit more in detail. So let me just bring up that notebook for you. So in this notebook, I've actually covered this particular part in a bit more in detail. Okay, so I wanted to take you through this notebook. And in this notebook, I've actually covered both the approaches. One, how you can query from a data frame, and two, how you can query from a SQL Server database. So both of those things I've actually done in this particular approach. So this is the other example I wanted to show you. Very similar, very similar. And in this entire thing, we are using LangChain. You can see LangChain is giving me access to all these things. We were talking about this create data frame agent. See, it is already a built-in function in LangChain. We don't have to do anything manually. We don't have to do anything manually. So LangChain already gives me the capability to work with it. Okay, so this is the thing. And similarly, we also have this SQL database toolkit. So this is how we will create a SQL agent. So we'll create a data frame agent and also a SQL agent in this exercise. The first step, define the language model. This is the Azure language model that you can instantiate and define. Next, what we are doing, we are reading the data frame. The data frame name is saheart.data. And we are creating the pandas data frame agent, the same thing that we discussed a while back. And you can ask it some question. Let's say, what are the different columns in my data set? If you ask it this question, what will happen? Okay, so we are asking the question, what are the different columns in the data set? So given the question, the model will be able to automatically frame the corresponding code for it. So given a question, the agent will be able to automatically figure out, the language model will be able to automatically figure out, okay, what is the code I should write? So df.columns. Okay, so if you know that df is my data frame, so if you have to do it manually, this is the syntax you will use to figure out what are the columns. So the columns will be listed out as a list, and the final result will be something like this. But as an end user, you will not see all this, right? You will not see any of this. As an end user, what will you see? Okay, as an end user, what will you see? Let me hide the output. Okay, as an end user, you will only see this thing. Okay, you will only see this part. So none of this part you will see. You will only see the last part. Okay, so similarly, how many missing values are there in the data set? You will get the only the answer like this. There are no missing value. But behind the scenes, what is happening? This is the Python syntax that is written. So df.isna is a way to check for missing values. Dot sum. Okay, and you can see this is very interesting. Can you display a brief summary of the columns? Okay, and if you can make it more advanced, you can make it more advanced. Like for example, this one. Show me that and distribution of age of people with this. Label the axis. Finally, comment on the principal trend observed. Look at this. It's a bit more in detail. So first, it will write the code to generate the plot. It will actually create the plot because there's a Python runtime that is also used behind the scenes, right? So when you ask this question in natural language, what will happen? This is like what I was doing in ChatGPT, right? You can ask a question, and GPT will generate the code. It will run that code, create the graph, and it will give you inferences about the graph. And all this is possible with agents. So you can see how we can build end-to-end systems with agency. You can create the histogram, and it will also comment that it's like a left skew distribution and all that. See, it actually explains what this graph is doing. Okay, so this is the heat map. Some of you might know what is a heat map in data science. Okay, so this is again technical topics, but the focus here is just to show you how to create it. So you can see when I say draw heat map to show correlation between all the columns, so it will generate the heat map. That's it. And the code behind the scenes is this df.core, sns.heatmap, cbound library is used to create the heat map, and then plt.show. Okay, so all this is written behind the scenes, and then it gives a small summary what the heat map does. See, this is a very detailed summary, very interesting. So it actually summarizes the heat map. Not only does it create the code, but it also creates the heat map, and it also summarizes the heat map. What are the key observations we are getting from the heat map? So this is the power of agents. They are not just language models. They are not just text completion engines. So the language model, if you ask it a question, it will just generate the code. Here we are not just generating the code. Here we are doing everything. I want to solve the problem. You do whatever it takes to solve the problem. I want to know this. I want to get the heat map and get some inferences. Summarize the trend. I want to solve the problem. So don't just write the code. If you do this in Gemini, what it will do? It will go and give you the code. But if you do this in a true agent, it will not only give the code, it will run the code and it will actually solve the problem. It will give you the output the way you expect it. Behind the scenes, it is calling multiple things. That's what it's doing. So this initial part was about how to query pandas data frame in Python. The next part of the demo is something which I believe will be much more relevant for everybody, is how to query databases. If you have a database, if you have a SQL Server database or an Oracle database, how can you have an agent directly query a database in natural language, using natural language? And there is a very simple open source way you can do it. So LangChain already gives me access to a SQL database. You can see. So we can connect to a, so in this case, what I'm doing is I'm connecting to a sample DB file. So I've given you a sample DB file and we are connecting to a sample DB file. You can take any database, by the way. You can take any database. Okay, so we are just connecting to a sample database. Just some quick checks we are doing. Sorry, actually what I'm doing here is, no, I'm actually creating a database. Yeah. Yeah, so I'm actually creating a dummy database. Okay, so creating a dummy SQL database, establish the connection, give it a database name, and create the table. This is the create table we are doing. It's an employee table I'm creating, and then we are inserting some values to it. So there are 4 rows in the table, right? So you can see that we have an employee table. There are 4 rows in the table. Very simple. And now what I can do, I am instantiating the agent, create SQL agent. That's it. This is again part of LangChain. So data frame, we had create data frame agent. Here we have create SQL agent. So what you do, you specify the name of the language model. You specify the toolkit. Toolkit will have the data BDB name and the LLM, and that's it. Straightforward. And you can ask a question, name the columns present in the database, and the answer will be this. Behind the scenes, what is happening? Behind the scenes, it is writing the, so behind the scenes, it is actually doing all this. This is the thought action observation chain you can see. It is listing out the tables, employee, right? And then employee table, it is figuring out how to get the columns and all that. See how it's actually able to retrieve all this. Okay. So what is the maximum salary paid to an employee to whom it was paid? This is a slightly complex query, right? So and very interesting. This is actually quite hard because in my database we only have a single table. You might have multiple tables in a database. Database can consist of several hundreds of tables, right? And it can have a very complex schema also. So if the language model is powerful enough, it will have the ability to even understand what table to query. But you need to give it a good amount of schema information. If the language model has access to the schema information, okay, and that will all be part of the system message. When you write the prompt, you have to write it in the system message. What is the schema and all that, right? This is the default one we are doing right now. But if you specify the system message correctly, and if you specify the schema information of your DB, then even if you write complex queries involving joins, inner joins, outer joins, involving 7, 8 different tables, it will still be able to do it for you. And that is what makes it so powerful. So the magic is again in the prompt. A detailed prompt, a detailed system message, you can do a lot of magic actually. Okay, so you can see what is the maximum salary paid. The answer will come out here, and this is the query that was written. Can you see how it methodically went about it? Select first name, last name, max salary. How it went about it. Okay, so this is just another small demo I wanted to show you. And now the objective would be I wanted to show you two other demonstrations, two other end-to-end demos involving two very real applications. You can see on the drive I've got something called e-commerce agent and stock agent. I'll show you these two end-to-end demos right now, how to design end-to-end agents from scratch. So far we have just seen generic ideas of an agent where it's a LLM plus tool. And now we'll actually see a fully functioning agent, how you can create the functions, how we can manually create the functions, how we can integrate the tools, and how we can have the fully functioning agents. Okay, friends, now we'll quickly see the solution, how we approach this thing. The use case is a very interesting use case where we are building a stock agent, and the objective of the stock agent would be to guide us during our investment decisions. So that is the end objective of what we are trying to achieve. So let me scroll all the way down to the end of the notebook to show you what the stock agent is capable of doing. If you scroll all the way down, this is what the stock agent will do for us. If I say, should we hold the NVIDIA stock? Should we sell or hold the NVIDIA stock? If I ask it a question like this, the agent will be able to answer. The agent will be able to answer. The final answer will be, please consider your investment strategy. And you can see it actually says, I'm not able to determine whether to hold it or not. This is very interesting. But maybe I can look at another question. Should we sell or hold the Johnson and Johnson stock? And let's see what it says. What is the final answer it gives? So it sees the recommendation is coming as hold the stock for now, but closely monitor. Okay, so this is the kind of agent that we want to build. This is the end result. But there's a lot of things we are doing behind the scenes. And part of this objective was to understand the process flow. That's why I wanted everybody to read the problem statement. So this is the process flow. Investors ask the agent whether to sell or hold a specific stock. The agent gathers relevant financial metrics, news articles, insider transactions, and market trends. And we will see later on that we will create tools for each of these things. So we will create a separate tool for the news stories, the latest news articles. We'll create a separate tool for the financial metrics. We'll create a separate tool for the insider transactions. Okay. Financial ratios are computed, insider transactions are evaluated, and sentiment analysis is conducted on the news. So this is a very powerful application where we will look at the news story. So next time I ask the question that should I sell or hold the NVIDIA stock? It will not only look at the current market indicators, but it will also look at all the news story concerning NVIDIA, and it will give me the recommendation based on that. So that is exactly what we are doing in this exercise. In my Python function that we will define shortly, we'll be able to connect to the news API, and we'll be able to get the sentiment of the news story, and based on that, the decisions will be taken. Okay, so it's quite an advanced use case that we are seeing. Okay. We also have the stock DB database is given to you, and this is consisting of all the typical financial ratios for all the different organizations. So all the different macro factors are present in my stock DB. Okay, so just to highlight that also to you. So you can see this is the overall process flow. This is the overall process flow and all the different tools that we will be creating. And maybe I can take a minute here to walk you through exactly what we will do as part of this exercise. Okay. So the first thing will be, this is the overall high level fin agent, right? So you can see this is the high level fin agent that we have. This is the overall fin agent that we are trying to create. So that's the high level fin agent that we are trying to create. And remember, I also told you what is an agent. An agent is LLM plus tools, right? So the fin agent will be driven by a GPT-4 Omni model. So there'll be an LLM which is nothing but our GPT-4, Omni model. This is the agent that is working behind the scenes. Okay. Sorry, this is the LLM that is working behind the scenes. And this fin agent will be consisting of multiple tools. So there are multiple tools that will be part of this agent, right? Let me write this a little better. So this is the GPT-4 model. This is the LLM that is working. So what is the LLM? The LLM is the GPT-4 Omni model. That's the LLM. And there are tools. What are the tools? There's the insider transactions tool. Let me write it down. Insider transaction, this is the tool. I'll put a square box around it, right? It provides data on insider trades. Okay. So we will actually use some kind of an API to do this. Okay. We'll get this data online. So we'll see this how to do this. Okay. There's a particular website we will connect to where all the typical insider transactions are historically listed. Because insider transaction is typically public data. So whenever an insider transaction is discovered, it will be listed out. Okay, so we want to take a decision based on the insider transactions. If too much of frauds are happening, then maybe that stock will not be a great recommendation. Okay, so we'll see how we can define this insider transactions tool, which will connect to some website and it will give me the relevant indicators from that. Okay, so that's the thing that we will see. We also have a tool for getting the current stock data. So this is the current stock data tool that we have. Okay, so what is the current stock data tool? It will give me the current stock price, the current stock data. So that is the tool we have for the current stock data. So let me just put a square bracket, and this is the current stock data, stock price tool. This is also an important factor, right? Because if you have to take a decision whether to sell or hold a stock, the current price matters. The current price matters because if the current price has increased a lot, then you might want to, kind of sell the stock to take the profits. Then we have a news agent. The news agent is something that we will create. So this is the high level agent, fin agent, but within the fin agent, there'll be a news agent we will create. And what will the news agent do? Agent is nothing but LLM plus tool. So this will again be driven by some GPT model and it will have tools. What kind of tool integrations will it have? It will connect to news websites. Some kind of news APIs it will connect to. Okay, so this is the entire agent we will create. So first we will create the news agent. Okay, LLM plus tools. And then this agent we will wrap it as a tool. We will wrap it as a tool and then we will use that tool as part of the high level agent. See how we do the workflow? So first we create the agent. We create the news agent independently and then we wrap it as a tool to use it as a tool for the high level, the top level finance agent. Okay, so that's what we will basically do. And the same workflow happens for the SQL agent. So we'll first create the agent. This is the same thing I showed you in the last demo. Remember there was a create SQL agent that is available by default in LangChain. So we will use the create SQL agent, which is a default in LangChain. So we will use the create SQL agent. And based on the create SQL agent, what we will do is we will go and write a query in English. And based on the English query, the SQL agent will generate the answers. It will generate the SQL query and give me the answers. Okay. And this is where the your SQL DB, the database, will be used. Okay. So it converts natural language into SQL queries. So it converts natural language into SQL queries to extract stock details, fundamental ratios, and technicals from a database, which I have already given to you. Okay. So this I will wrap it as a tool. So the end result would be, so first I will create these 4 tools and then we will wrap these 4 tools and wrap it as and create this final agent. So this is going to be the end result of this exercise. Okay, so I just wanted to show you the whole workflow, because once we have the whole workflow at the back of our mind, the implementation is very, very straightforward. So I'll quickly breeze through the implementation. Okay. So first we are instantiating this one, the LLM, the language model you can see. And here we give a very detailed system message. We did not see this before, because before we were using default system messages, but here we are giving a very detailed customized system message as to what we want to do. Even for the create SQL agent, we are giving a customized, system message. You can see this is what we are doing. And here goes the create SQL agent. We already used this in the last demo, but the only additional part is we are giving the prompt. Otherwise, before we were using the default prompt, but here we are giving a specific prompt, what we wanted to do. That's it. And now, next part is I told you we have to convert the agent to a tool, because we want to use it in our fin agent, the main agent. Okay, and agents can only use the tools. Okay, so you can see that we are wrapping it as a tool, and it is nothing but we are creating a function. Okay, so this is that SQL agent.invoke we are doing inside the function. This is that agent we created, and we are wrapping this as a function. Okay, I told you already that this use a simple Python function to create a tool, right? So this is the SQL tool that we instantiate. And this part is very, very important. You have to describe the tool very effectively, what the tool is supposed to do. So the tool description is very important. And this is what the large language model, the main fin agent, will see to take decisions. So when you are asking the fin agent a question, when you're giving it a query, it will look at the description to decide which tool to call. So that's the thing that we are actually doing right now. Okay, so now moving on, we can test the tool. What are the fundamentals of Apple ticker symbol AAPL for today? And given this question, the SQL agent will go through the database, and it will try to find the relevant queries, and it will answer that question for you. Okay, it will actually give you all the fundamentals for Apple. Okay, so you can see this is the answer it will give you. Provide me the financial information of Microsoft, like revenue, profit, and EBITDA for today. And you can scroll down and you can see what kind of answer it is giving. Okay, so this is the first SQL tool that we created. Second, we're creating a news research agent, and then we will wrap it as a tool. How do we do that? Let's see. So we will define, we will again wrap it as a function. And remember the news, there are two types of news that we will have. There are two types of news that we will have. One is there'll be a company news, and second, there'll be an industry news. Both are important, right? Let's say if we talk about NVIDIA, NVIDIA is a company, but what is the industry of NVIDIA? Semiconductors. Okay, so we want to know how both are performing. What is the sentiment of both? So not just the company, but even the industry also matters. So the company is okay, that's one part, but even the industry matters. So if you talk about the FMCG industry, not all the companies are doing well, right? If you talk about the semiconductor industry, not all the companies are doing well. NVIDIA is doing very well, but are all the semiconductor companies doing well? No. So both the things matter. Industry news matters, company news matters for me to take a stock specific decision. Okay, so now moving on. And we are actually using some kind of an API here. I won't take you through all this right now. You can go through this all, but this is actually where we are creating the function. And within the function, I explicitly define the company news and the industry news. And the end result, what I do is I wrap it as a tool. If you see what I do is, let me scroll down and show you. This is the part where I'm wrapping this whole thing as a tool. Okay, so we create the final news agent. See, the news agent is a combination of the two tools, right? You can see this is the news agent that we created. So the agent, the LLM, and the tools. What are the tools? The tools are company news and industry news. So we created those two functions, right? So first we create the news agent, and then we convert the news agent to a tool. Okay, this is how we convert it to a tool. And now we can simply call the news agent tool, the top level news agent tool. And when I do that, when I give an argument of company NVIDIA, see what it does? It actually is able to find out the real-time company news of NVIDIA. And it is also able to find out the real-time industry news of NVIDIA. So it does two things. First, based on the company, it finds out what is the industry. Industry keywords are semiconductor, AI, GPUs, technology. And now it's able to find out. So this is NVIDIA specific insights. And this is in industry specific insights based on this thing. It is using also a kind of a retrieval augmented generation technique. So it's looking at those keywords, fetching the relevant news stories, and summarizing the information for me. So that is how this entire news agent will work behind the scenes. And the final end result will be something like this. Okay, create a tool to fetch insider transactions. And I told you there's a website from which we are taking this. So this is how we are getting the insider transactions tool. And similarly, we are also creating the this thing, the last part, which is for the current stock price. Okay, so the current stock price is what we are getting from Alpha Vantage, and insider transactions is what we are also getting from this thing called Alpha Vantage. And now we will create the top level Fin agent. Remember, we have got 4 tools that we have separately defined. And now that we have defined the 4 tools separately, now we will create the top level Fin agent. So that is what we are doing now. So we have the SQL tool, the get stock price tool, the insider transactions tool, and the news tool. Okay. And so we simply combine these tools, and this is how we create the final Fin agent. Okay. So remember, the agent is a combination of the LLM, the language model, the tools, and the prompt. The prompt is the React prompt. And this is something we already created. This is nothing but the entire prompt, which consists of the system message, the user message. We call it a human message, actually. This is, again, a specific syntax thing. So user message is also called human message. And this is part of the whole prompt. And now that this is ready, you can test out the final Fin agent. Okay. And this you can actually deploy as an application. The first part is you will create all of these things. And the next part is you will take all this and deploy this as an application. So that is something that I will briefly show you in some time from now, how to actually create a fully functioning application. But I hope all of you are getting the flavor of the demo, how we are actually integrating all the different components and what makes agents so powerful. So ultimately, the thinking engine is still the large language model. The large language model is the one responsible for taking the decisions and for the entire thought process. But you can see that at a high level, this is what is involved. Okay, you can see. I wanted to show you one more example very quickly. I wanted to show you one more example with respect to an e-commerce, end-to-end e-commerce chatbot. This is very similar, and you can just give it a glance what we are trying to do here. And what we are trying to do in this particular in this particular e-commerce chatbot is we are trying to, customers are asking questions, and based on customer questions, you are trying to give them information about products, about orders, about refunds, and all of these kinds of things. So based on the customer questions, you are able to, you're effectively able to give them, uh, you're responding to their questions, product inquiries, policy inquiries, and things like that. Okay, so the overall idea is very, very similar. At a high level, we have got 2 different things here. So we have a database, and on this we will use a data frame agent, right? So we have a database which will consist of the typical orders information. Okay, so when you order something, you have the products, you have the product catalog. So all that will be part of the database, right? So the ecom DB will contain all the product specific data, the order specific data. All that will be there in the ecom DB. It's a transactional database, right? Let's say. So you will create a SQL data frame agent on top, create SQL agent on top of that. Users can ask questions in natural language, and the answers will be fetched from the database. We already saw multiple times how to do that. We also additionally have a policy docs file. The policy docs file, it has some kind of product information. Okay, so the policy docs file has some kind of product information. Okay, it is used for policy inquiry, product inquiry. So if you want to ask something about return policy, okay, so some user has reached out and saying, okay, the return policies are what? So that is part of the policy docs, and you can see, you can actually download and check what content is there. Let me show you. Let me show you what content, and why am I showing this to you? Because this is where we will use a RAG tool. We discussed RAGs extensively in the initial part of our session, and that time we only created RAG applications. But now what we are trying to do is we will create a RAG application, we will wrap it as a tool, and we will use it as part of an agent. So this is a end-to-end demo where we are using RAG as part of an agent. I hope you are able to connect the dots well. Okay, so you can see this is the policy docs that we have right now. Okay, actually it's a vector DB. So the documents are not given, but the indexing part is already done. You can see that when I open up the policy docs, when I unzip the file, inside that we already have the chroma DB that is created for us. Okay, so the vector DB is already given to us. So basically, we already have the embeddings and the chunk embeddings and the text is already given to us. Okay, so this part is already done. But any which ways, this further tells us that this is the RAG-based approach. So we will use a create SQL agent to get products information from here, and we will use a RAG-based approach to get the policy information from here. So these are the two tools that we will create. Rest of the workflow is very, very similar. You can go over it. So see, this is the create SQL agent that we are creating. And if you come all the way down, this is the part where we are creating the RAG tool. So first you instantiate the RAG. Remember the vector DB creation is already done. We already have the vector DB created here. So no need to do the indexing part. It is already done. And we are simply doing the loading. We are simply loading the vector DB. See, this is the part where I'm using Chroma to load the persisted DB. Okay. And then we define the RAG system message, user message template, retrieve the top 5 chunks. Retrieve the top 5 chunks. And then we go and wrap it as a tool. Tool is nothing but a function. So whatever thing we did in the RAG, we wrap it as a tool. And here we are simply testing the RAG. Okay, so what is the RAM on the mobile phone? So what it does, based on the user query, we are going to the vector DB, retrieving the top 5 relevant chunks and answering the question. This is what we already saw. But now the only thing is now we have a RAG tool. And this we will eventually use in the whole agent. We created a few other tools to capture feedback because honestly, what happens is when you're interacting with a real chatbot in the e-commerce or Amazon, whatever, you will actually at the end when you close the chat, they ask you for feedback. So this is the final feedback collection, the survey collection that we do. So this is a small tool that we create, a function that we create to register feedback, and we create one more function for defer to human. Like for example, logs customer details and reason for deferring to a human agent. Sometimes the e-commerce bots will say, okay, do you want to talk to a human being? So this is another function that we are creating for that. These are some external functions that we are creating. This is for logging and stuff. And then finally, this is the most important part. We are creating the final agent here. And you can see we have got 5 tools with us: SQL tool, RAG tool, defer to human, register feedback, and daysins. Okay, so these are the 2 most important ones that we saw, and the other was generic tools that we created. And this is the whole agent that we have. And now you can actually see how to work with the chatbot. See, this is how the chatbot will work. When I say chat with agent, you can see how the chat agent will work now. So, hi, how can I help you? I want to check my orders for the last 2 months. This is the complete agent, right? So given the user query, the agent will figure out, this is using a React framework, thought, action, observation. The agent will figure out what tool to use. So the user wants to know the order from the last 2 months. So that means SQL tool has to be used because the order information is present in the SQL DB. So the agent will be able to figure out that, okay, it seems that there are no orders placed by you. Done, completed. Okay, next, I want to buy a keyboard. Do you have any? So now the RAG tool will be called invoking RAG tool. So go and look up in the vector DB, what are the relevant things with respect to keyboard and return the information. Okay, so finish. We have the premium keyboard and all the details are listed out. Okay, straightforward. Return policy, cancellation policy, warranty, all the policy related stuff is written down. And this is the complete answer that you will get. And finally, what will happen? You can see, no thanks. You want to purchase. If you have any other questions, feel free to ask. No thanks. When I say no thanks, what will happen? Thank you for considering. Rate it. This is the feedback tool getting called. Can you see? So based on your answer, the agent is able to figure out that okay, the user wants to end the chat. Okay, so now we call the feedback tool. You give a rating, and that will be registered in the feedback tool. So can you see invoking register feedback? The feedback will be registered, and the chatbot chat will complete. So this is how you can think of a fully functional complex chatbot. Okay, so when we interact with a chatbot is usually it's a kind of a very complicated agent, but there are multiple tools that are working behind the scenes. And this demo was to give you a very basic idea in terms of how to think about an agentic kind of a system, a really real-time kind of a chatbot. When you think about it, this is actually how things are working. All the pieces are working behind the scenes. Okay, and I hope this gives you a good amount of clarity in terms of how things really happen in the real world.